Good morning, everybody.
Hey.
Thomas, do you want to try projecting your screen already, or?
Yes.
Yeah.
Can you hear me?
Yeah.
Okay, good.
And I think I enabled screen sharing for all panelists, so you should just be able to do that.
Okay. Can you see my screen?
Yep.
Okay, I'm trying to make it full screen.
Yep.
Can you see the slides moving?
Yep. You're now on slide 3, 4.
Yeah. Okay. Can you also see my mouse pointer?
Not at present. Where is it?
It's below the title of the slide.
No, I can't see that.
Okay.
I can see your list of participants with me in the video feed as well. So that's hiding a little bit of the screen. Yeah, now it's just small, and if you move it, yeah, that's better.
Okay. Is anybody else here already wanting to test sharing the screen, or should I just leave it up?
I'm not sure the second speaker, at least of the first session, is not here yet. So maybe you can just leave it up for now.
Okay.
When he logs in, maybe we can. Yeah, let's see when he logs in. Morning, Peter. I just made you co-host again, just like yesterday.
Good morning. Thank you. Who's chairing this session? Am I chairing the session?
If you want, yeah, go ahead. Just let me know when you want to start so that I can press the record button.
Oh, I have no opinion. And Thomas is clearly here with hopefully working audio.
Yes, can you hear me?
Yeah, that's good.
Hi guys, this is Dan. I just came to check if everything is working properly.
As far as we can tell.
Yep.
Yeah,
Everything
thank you.
seems fine.
Okay, great. And the YouTube stream should be less delayed now.
Yeah,
Is that
thanks. I saw your message. Yeah.
okay? So there's no problem with that. That's great.
Yep.
Then I'm gonna leave, and you can just message me if you need me for anything.
Yeah. Okay. Thank you very much for your help.
My pleasure. Bye bye.
Bye.
Okay, I guess we should get started. Lena, could you record?
Yep, I'm now recording.
Thomas. Thomas Bauerreis will give our first talk.
All right, thank you very much. So I'll be talking about for modeling and proof for Cherry ISAs. And this joint work of a large number of people across different organizations. And if you look at the Cherry project as a whole, there are even more people who are not listed here, working on Cherry hardware and software, for example. And I try to give a bit of context about Cherry as a whole, but the talk will focus on the formal modeling and proof work. So as a motivating data point, here is a chart from a Microsoft report about security vulnerabilities that they have patched. And the number of the percentage of those that are due to memory safety issues. And that number is quite high at around 70%. And what's more, this percentage has remained relatively stable over the years. And this seems to be quite common. So Google, for example, is reporting similar numbers. So memory safety bugs are still a major source of security vulnerabilities. And there are two fundamental problems contributing to this. So typically, hardware and software is developed using test and debug methods. And those are not well suited to find bugs in corner cases. And the other problem is that even small bugs can lead to serious security vulnerabilities. And mainstream hardware architectures and the language abstractions provided by C and C++, which are typically used in system software, don't provide good mechanisms to mitigate those bugs. So you only get very coarse-grained memory protection via the MMU, for example. Cherry tries to address this second problem by adding new security primitives to the instruction set architecture, the ISA. That's the interface between the hardware and the software. And these new security primitives, they are implemented in the microarchitecture of the processor, and they enable new security behavior in software. So Cherry adds a capability mechanism to the architecture. And this can be used to provide fine-grained memory protection and scalable software compartmentalization. I'll talk a bit more concretely about that later. So Cherry provides this architecture protection model, and this can mitigate many known and possibly even some unknown classes of vulnerabilities, mainly in C and C++ trusted computing bases like operating systems, language runtimes, browsers, and so on. Cherry is being developed at Cambridge and SRI International since 2010, and has been supported by government research funding, but there have also been collaborations with industrial partners. In particular, ARM is currently building a prototype ARMv8 CPU with some Cherry extensions built in, and they will ship a development board with that processor next year. So that's pretty exciting. So Cherry, the architectural protection model of Cherry addresses this second fundamental problem that I mentioned. There is also the other one, small bugs in corner cases. And especially when we build security primitives into the hardware, we have to make sure that those mechanisms don't have bugs in corner cases. So we use formal methods for this. So it use not just prose architecture specifications, but we also have formal models of the architecture specified in the L3 and SAIL languages. And these models enable some immediate lightweight uses of the models, for example, for testing hardware implementations against the formal model used as an executable test oracle, or also for test generation. And can also use these formal models then for formal verification. So we formalized some key architectural security properties, and then we prove that the architecture satisfies those properties. And we mechanized our proofs in Isabelle Hall, a proof assistant, and this makes sure that our proofs are correct and we didn't forget any corner cases in our proof. Right, so let me give a bit of context about Cherry. You can think of the Cherry capability mechanism as providing a protection semantics for pointers. So it enforces integrity and provenance validity for pointers. So software cannot just forge arbitrary pointers. They have to be derived from existing ones via valid operations. And invalid pointers cannot be used. Cherry also adds bounds and permissions metadata to pointers to basically limit what software can use a given pointer for. And it also enforces monotonicity of capability manipulations. So you can narrow down the bounds and permissions of pointers, but you cannot grow them to escalate your privileges. So when a Cherry system starts up, the hardware will provide some initial strong root capabilities. And then the operating system and the language runtime can successively narrow those down when handing out pointers to enforce security policies. So you can, for example, isolate a software compartment by only giving it pointers with bounds restricted to a certain memory area. So this protection semantics for pointers is implemented in the microarchitecture using a new hardware capability data type with hardware checked and unforgeable bounds and permissions. And also the memory is modified to store tag bits that store the validity of capabilities. And over the years, there has been a co-design process of hardware prototypes, formal models, and software stack to make sure that this capability mechanism integrates cleanly into existing hardware and software stacks. The first target architecture of Cherry was 64-bit MIPS, and this is still being maintained as the baseline Cherry architecture. But the mechanism is designed to be portable to other architectures as well. So there is now also an instantiation for RISC-V that is under development. And as mentioned, ARM is currently building a prototype, the Morello board. And for this, there is some significant amount of funding from ARM as well as from the UK government as part of the Digital Security by Design UKRI research program. So the ARM Morella board is expected to ship next year. It will include a processor based on the Neoverse N1, a quad-core CPU, and it will have Cherry extensions built in. And this will allow basically evaluation of these Cherry mechanisms on a high-end CPU. And various of these Cherry features will be configurable at runtime to allow software experimentation and explore some trade-offs between performance, security, and compatibility. And based on the results of those experiments, some subset of the capability features might end up in future versions of the ARM architecture. Here's another example of a RISC-V microarchitecture in this case. So this is a microcontroller based on the open source Piccolo CPU. And you see some modifications done here to implement Cherry. So there are modifications to the memory subsystem to store and transport tag bits. There are modifications to the register file and controller registers. For example, the program counter register becomes a program counter capability register. New exceptions have been added. So when a bounce check fails, for example, there is a new kind of exception. And additional logic has been added to support the capability manipulations, the new capability instructions, and modifications to existing instructions. So there's a lot going on the hardware side. There's also work on the software side. So early on, getting software to run on Cherry hardware required a bit of manual annotation of the source code. And there was some focus on hybrid modes of operation of capability aware and capability unaware code. But over the years, there has been quite a bit of effort going into tool chains, so compilers and linkers. So today, the use of capabilities has become much more automatic. So ideally, in many cases, it's sufficient to just take existing source code, C source code unmodified, and use the Cherry C compiler, and you will get a binary that makes use of capabilities. And quite a bit of software has been ported to Cherry. So there is a complete operating system, so a FreeBSD kernel and user space with some system libraries and tools, and also applications like a database, web server, and WebKit. So this stack is running with capabilities being used throughout the stack. So this was a quick overview of the Cherry project. If you like more information, there is a website which also has more documents, like an introduction to Cherry or a C and C++ programming guide. And there's also a paper on formal modeling and proof for Cherry, which has been presented at IEEE Security and Privacy last month by Kindelan Nienhaus, who has done the proof for Cherry MIPS. And this formal modeling and proof work will be the focus of the rest of this talk. So let's look a bit closer at how this Cherry's capability mechanism works. Here's a small example C program with two global variables. And let's say that one of them is confidential. And in line 4 of this program, a pointer is taken to the public global variable. Then there is some pointer arithmetic, and then the pointer is dereferenced. Now, in the C standard, it's not defined what object this pointer refers to after this pointer arithmetic. But what's quite likely to happen in practice is that these global variables will be allocated next to each other. And after the pointer arithmetic, the pointer P will point to the secret key variable, and it will get dereferenced, and the program will print out the value of the secret key variable. Now, if you take this program and compile it with a Cherry C compiler, then taking the address to the variable, taking a pointer to the variable x in line 4 will give you a capability, and the compiler will make sure that the bounds of that capability will be restricted to this, to the variable x. And the pointer arithmetic on line 5 is still possible, but then on line 6, when you try to dereference the pointer, the hardware will perform a bounds check. And this will fail in this case because the pointer is now outside the bounds of the capability, and it will raise a out of bounds exception. And your program will be aborted before it can print out the value of the secret key in this case. So this basically turns some undefined behavior in the C program into a trap behavior that traps and aborts the program. As I said, the hardware enforces that capabilities can only be manipulated in certain ways that preserve monotonicity. So you can change the address, for example, of a capability, or decrease its bounds and remove permissions. And if you try to tamper with capabilities in other ways, for example, by modifying some of the bytes of the in-memory representation of capabilities, then the hardware will clear the tag bit, rendering the capability unusable. So you can use these mechanisms for fine-grained memory protection, as we've seen here, protecting this pointers to this variable x. You can also use it on a somewhat bigger scale for software compartmentalization. So you can set up, you can isolate two compartments from each other, for example, by only giving them capabilities to disjoint regions of memory. Or you can allow some controlled sharing of data between compartments. So one compartment can delegate some of its capabilities to another one, and then they can share a data buffer, for example. And there are also mechanisms for transferring control between compartments without handing out unnecessary privileges. So if compartment A wants to allow another compartment B to invoke some of its code, then compartment A can construct a capability to an entry point of the code and seal that capability. So that's an operation that you can do on capabilities. And when compartment A can then pass on the sealed capability to compartment B, and B can then, the sealed capability can then not be used by B to perform any memory accesses in the compartment A. The only thing that compartment B can do is invoke the sealed capability using a instruction of the Cherry processor. And this will, in hardware, atomically unseal the capability and jump to it. And then, so this will allow compartment B to invoke code in compartment A without gaining any direct access to memory within compartment A. All right, so these are some of the mechanisms of Cherry. Now we would like to reason about those, so we need some formal architecture models. And apart from formal proof, as I said, these formal models also have some more immediate lightweight uses. So in contrast to a prose architecture description that is somewhat disconnected from the hardware implementation and the software stack and the test suite, we use formal models, and we also use those models as executable test oracles for hardware implementations and for bringing up software directly above the model. So this has been quite useful. It also doesn't have to be hard to get such formal models. So it doesn't necessarily require formal methods expertise to write a formal architecture model in the Sail language, for example. And in the Cherry project, we've gotten to a point where people on the Cherry team working on new Cherry features who would normally write prose descriptions now routinely develop the formal model, the SAIL formal models. And there are more lightweight uses of the formal model. So you can also use these models in documentation. So in fact, the SAIL specifications of the instruction behavior are inlined into the architecture document. You can also use the formal model for test generation. So Brian Kettle in Edinburgh has been using a combination of symbolic execution and constraint solving to generate test cases that achieve good specification coverage. And finally, you can also use the formal model for experimentation with design alternatives. So this was useful, for example, when designing the compression scheme for the in-memory capability representation. It was useful to do this experimentation with the formal models without needing to implement these in microarchitecture. Here are the SAIL models of the cherry architectures that we have. So there is the cherry MIPS model, which is handwritten around 7,000 lines. There's also the cherry RISC-V model, which is an extension, or it's based on the SAIL model of the RISC-V base ISA, which, as Alistair has mentioned yesterday, has been adopted by the RISC-V Foundation as the official formal model. So on top of that RISC-V base specification, there are around 4,000 lines for the cherry extension. And both cherry MIPS and cherry RISC-V are available on GitHub as open source specifications. And as mentioned, there is also the cherry ARM Morello specification. This we have received from ARM in the form of an ASL specification. That's the specification language that ARM uses internally. And we have some tooling that semi-automatically translates this from ASL into SAIL. And the size of that specification is around 100,000 lines of SAIL. So this is the biggest specification that we have. Right. Here's an example of a SAIL specification of the capability load instruction in cherry MIPS. So at the beginning, it checks that capabilities are enabled. Then it reads a capability from a register that is supposed to authorize this memory load. Then it performs some checks, including a bounce check on lines 10 and 11. And then on line 15, if these checks have succeeded, it performs the load and then writes the result to the destination register. Right. So we have these models written in SAIL. So let's talk about some security properties that we can formalize and prove. So looking at the PROS specification, there are some properties that are explained there, like the monotonicity property of capability manipulations that I mentioned already. And these are described informally. There are also exceptions to that monotonicity mentioned in the specification. So one of those exceptions is invocation of sealed capabilities. So this mechanism that I mentioned, where a compartment can invoke code in another compartment. This is basically a domain transition mechanism. And after this atomic unsealing of the capabilities, this might be a non-monotonic increase in the set of available capabilities in the new state. Similarly, also, when an exception gets triggered, you typically end up in a exception handler in the operating system. So this is also a transition to another protection domain. So when we want to prove that the architecture has these properties, we need to formalize them. And we did this formalization of these hold ISA security properties. And we proved that they hold for executions of arbitrary code. And we conducted machine check proofs using Isabelle Hall. And the proof is structured into layers. On the lowest layer, we define an abstraction of cherry, and on top of which we can then layer proofs of higher level security properties. So this abstraction is formulated in terms of abstract actions related to capabilities. So we have actions for each type of capability manipulation. So restricting capability by narrowing its bounds, or removing permissions, for example, or sealing and unsealing, or invoking capabilities. And there are also actions for memory accesses, which require a authorizing capability. And finally, there's a separate type of action when an exception gets raised. Then map the instructions of the architecture to these abstract actions. Some of them will not have any actions related to capabilities. So if you take an integer arithmetic instruction, for example, this will not have any capability actions. But instructions for changing permissions and bounds will have a restrict cap action, for example. This CMOV-Z instruction is a conditional one, so it might have an action only if a certain condition holds. These last two instructions are instruction of the legacy MIPS ISA. So these are legacy store instructions. And these legacy instructions have also been modified in Cherry MIPS to use an ambient default data capability, the DDC register, as an authority for this store. So this is made explicit in these actions. And then we formalize requirements for those actions. So here's one for storing data. So, so if you have an instruction in the state S leading to a state S prime on line 4 and line 5, that has a store data action to a given address A with length n, ln, and with a given authorizing capability, then we require that the tag bit of this authority capability must be set, so it must be valid. The capability must not be sealed and must have the store permission. And the addresses that will be affected by this data store must be within the bounds of the capability. Moreover, on lines 12 to 14, if this store modifies any part of a capability in memory, then the instruction must make sure that the tag of the capability gets cleared, because this is just a pure data store, not a capability store. Right. And we've formalized properties in a similar style for all the other capability actions, and then we proved that the Cherry MIPS is actually, so these properties are satisfied for all the Cherry MIPS instructions. So Cherry MIPS is an instantiation of this abstract model. And we've conducted this proof with respect to the L3 Cherry MIPS model. For the SAIL models, SAIL by default generates theorem prover definitions that use a slightly different interface. So instead of a state monad as used by L3, it uses a free monad of effects. So register reads and writes and memory loads and stores. This was originally motivated so that instruction set architecture specified in SAIL can be connected to relaxed memory models for reasoning in a concurrent setting. And we have not done that yet in this Cherry context, although this might be interesting future work, looking at Cherry in a concurrent setting. Nevertheless, we found this interface useful for formulating requirements. So you can use this for each instruction to basically get the set of possible traces of register memory effects. We used this to formulate requirements on those traces of effects. So this is an iteration of the abstract model compared to the version that we used for L3. And we formulate requirements on effect traces of instructions. For example, if at any point in those traces a memory store is performed, then at some point beforehand in the trace, a capability must have been read by the instruction that authorizes this store. This would be corresponding to the property that we've seen before for storing data. There are also other requirements like about access to privileged registers and deriving capabilities. Here's an example of that, looking at the capability unseal instruction. Here you see some snippet of the sales specification of that instruction. It reads two capabilities. One of them is supposed to be sealed, and the other one is supposed to authorize the unsealing of that capability. Then some checks are performed, and at the end, if those checks are successful, the unsealed capability is written to the destination register. And if you look at the effect trace that this basically generates two register reads and a register write. And the property that we require to hold then says that every time a capability is written to a register, unless an exception or capability invocation occurs, we have to make sure that this capability that is written must be derivable from capabilities that have been read before. And this derivable predicate is defined in the abstract model. It allows it specifies the allowed capability manipulations. And in this case, it will give us proof obligations that the checks that the sales specification of the instruction performs are actually what we require in the abstract model for unsealing capabilities. Right. So we instantiated this model for this abstract model for the concrete sale models of the Cherry MIPS, Cherry RISC-V, and Morello architectures. We've completed a proof for the Cherry MIPS model, corresponding to the one about the L3 model. And now work is ongoing on finishing this proof for Cherry RISC-V and the Morello specifications. Right, so this was basically the lowest layer of the proof. And now that we have this abstraction, and once we have proved that concrete ISA satisfies this abstraction, we can prove higher level properties just in terms of the abstraction. And the property that we've proved here is basically a characterization of the capabilities that a compartment can construct and an upper bound on that set of capabilities. So this set of reachable capabilities, as we call it, is defined inductively. In the base case, you start with the capabilities that are available in registers that are accessible to the compartment. And then you have inductive cases where you can construct new capabilities starting from that. So if you have a reachable capability that authorizes the load of a capability from memory, then you can use that capability as well. You can use reachable capabilities to seal and unseal if you have another reachable capability that authorizes it. And you can restrict capabilities. But we deliberately do not include protection domain transitions here. So this is supposed to characterize the capabilities that are reachable within a compartment. And then the property that we prove is that this is indeed an upper bound of the capabilities that are reachable. So if you have a trace of executing a sequence of arbitrary instructions, starting from a state S leading to a state S prime, and this trace of instructions does not perform a domain transition. So this is basically a sequence of instructions within the compartment. Then the capabilities that are reachable afterwards are a subset of the capabilities that were reachable at the start. So this is a formalization of this monotonicity property. By executing arbitrary code within the compartment cannot increase the set of capabilities that it has available. Right. There's also an assumption here that so this makes explicit also some other assumptions. Here we assume that the compartment does not have access to system registers, because this would might allow, for example, changing control bits of the architecture, like address translation, changing the address translation mapping. This might invalidate this property. So we have some assumptions here. Right. We can then go on and use this monotonicity property also to look at a more concrete scenario. So we looked at a compartmentalization scenario where you have a compartment that we want to isolate. And we assume we want to isolate it to a specific region of memory, which is depicted here as just a contiguous region of memory, but in practice, it does not have to be contiguous. It can be some set of memory addresses, basically. Here's the formalization of the assumptions that we have in this scenario. In the interest of time, I'm not getting into too much detail here. Just want to point out on line 4, for example, we assume that all the capabilities that are accessible in registers and in this memory region that we grant to the compartment, the bounds of those capabilities are contained within this set of addresses. So the compartment does not have any capabilities that point outside the compartment. The only exceptions that we allow on lines 5 and 6 are sealed capabilities that this compartment cannot unseal. So we allow the compartment to have some sealed capabilities that it can invoke to invoke code in other compartments, but not perform any memory accesses outside of the compartment. This is a formulation of the guarantees that hold after executing a sequence of arbitrary instructions in the compartment up to and including the point of domain transition. So what holds then on lines 2 and 3 is that the program counter points to an entry point in another compartment or to an exception handler, depending on which kind of domain transition has occurred. We also can guarantee that the compartment has not changed any memory contents outside of the set of addresses that we have granted it access to. And also, since we assume that it does not have system register access, we can also say that the special capability registers do not change the value. And then we can put this together into a property that holds for arbitrary execution of arbitrary code in this scenario. Right. So we have proved this for cherry maps. Here are some statistics about this proof. So it took around 30,000 lines of proof in Isabelle Hall. Although a significant part of this, around 16,000 lines, have been automatically generated. So in particular, proofs about most of the instructions are automatic. The manual proof effort is focused on some of the core parts of the architecture, like auxiliary functions for manipulating capabilities. And if you load this proof into Isabelle, it takes around 25 minutes to process. All right, so we have proved these properties, and so far the properties we've proved, they talk about execution of completely arbitrary code, which is definitely useful and necessary, but there is more to be said about other security properties, for example, about more constrained code. So one recent work going in that direction is work by Laus Gerstengard and others about a capability machine and code following a certain calling convention that guarantees well-bracketed control flow and local state encapsulation. And so it would be useful to have to prove more properties like this, but proving this with respect to full ISA models will likely require some more powerful and scalable proof techniques. So the proof technique used in that work was using logical relation with respect to a idealized capability ISA. Would be interesting to see what would be involved in scaling this up to full ISA models. All right, to conclude, we showed how we applied more rigorous engineering in the cherry design process. We show how we used formal models to formalize and prove key security properties of the architecture. We've done this for cherry MIPS and are now doing it for cherry RISC-V and Morello, the cherry ARM prototype. And you're invited to look at the cherry website for more information on that. Thank you very much.
Okay, thank you. We have a couple of talks already. Sorry, a couple of questions already. So Julia Belyakova asks, could you please explain again how SAIL interacts with Isabelle whole, if anyhow? Are they in different layers of the proof?
So you have these architecture specifications that are written in SAIL, and then SAIL basically has a can generate theorem prover definitions. And for Isabelle whole and for whole 4, this goes via an intermediate language, LAM. So the SAIL tool basically outputs LAM definitions, and LAM can then translate these to either Isabelle whole or whole 4 definitions. And as I said, the interface that is used there is so the imperative specifications of the in SAIL are translated to monadic definitions in the theorem movers. And in SAIL, you can choose to either use a state monad or this effect monad that I've been talking about. So that's basically the interface there.
Okay. And Jahoon Kang asks, system software often manipulates pointers very widely, e.g. pointer tagging, hashing pointers, compressing and decompressing. Does Cherry support such wild pointer manipulations?
I think the Cherry team has taken quite a bit of effort to support common idioms of uses of pointers in Cherry as well. So some of these, pointer tagging, for example. So I know that in ARM, there is this mechanism for pointer tagging, and when designing this Cherry ARM extension, there has been quite a bit of care that had been taken into account when looking at this. So you have to take care that these bits of the pointer that are used to store additional information are not used for bounds calculations and things like that, for example. So care has to be taken there. But in principle, it's possible to support mechanisms like this as well in Cherry. Let's see.
Matt Dubinsky asks, is there a path to formally prove prevention of side and covert channels in microarchitectures implementing Cherry ISAs?
That's would definitely be interesting. We haven't looked at this in detail so far. So the proofs that we have done, they are about the architectural level. So they deliberately do not talk about side channels. But yeah, it would definitely be interesting for future work to look at this. Yeah.
There is a technical report that you can get from the Cherry pages that discusses non-formally the interactions between Cherry and Spectre and Meltdown attacks. Leonard asks, as a follow-up to Jehoon's question, does Cherry's notion of pointer provenance directly extend or embed C's pointer provenance that we heard about yesterday?
So I'm not sure if it's a direct implementation, but as we've seen in this example, so this was a case where we had some undefined behavior in C, and basically if you want to detect this undefined behavior, you would need to track the provenance somehow, and to some degree, the basically the balancing capabilities can do that. So as we saw in that example, you had bounds that were restricted to the extent of the language level object. And then if you move outside the bounds, then the hardware can detect this, which corresponds in this case to checking in the C semantic on the C semantic level, this is an out of bounds access or not. So I guess to some degree, whether this is a direct implementation, I don't know enough about the C standard to say something definitive there.
Maybe I can add a bit. So I think so this is not something that we have proved, but my intuition is that for simple cases, the two more or less coincide. But then if one looks in the corners, there are some subtle differences. So for example, well, and they're differences in some of the places where it's not clear what C is. So for example, the Cherry design is quite careful to allow some out of bounds pointer construction, more than just one passed objects, because we see that real code does that. Although in ISO, that's clearly undefined behavior. And then then you have a bunch of choices as to whether, how you deal with sub-object provenance on the C side, and how often, how aggressively you narrow capabilities on the Cherry side. So there are quite a few interesting questions. What you can say is that the Cherry systems folk have ported quite large bodies of low-level systems code to Cherry with quite mild changes to the source code. Dominique asks, Dominique de Vries, do you think you could apply your results to reason about the code for a real system?
So I think our results might be part of that proof. So as I said, the properties that we prove talk about execution of arbitrary codes, arbitrary code within a compartment, for example, up to the point of a domain transition. And then when a domain transition happens, if you jump to the operating system, for example, then if you want to have a property about the full system, you would also need to say something about what happens on the operating system level. So you might have to connect that to a proof that of properties about the operating system code. So I think if you want to have proof about a real system, there's definitely more that needs to be done. But I think the results can be a part of that. That answers the question.
Okay, we have at present no more questions. Just leave it for a few seconds. Dominic DeVries, can you elaborate on your next plans?
So the immediate next plans are to continue these proofs, in particular for Morello, this Cherry ARM prototype. As I said, ARM plans to ship a development board with that processor next year, but the architecture is currently being finalized. Our goal is to basically complete as much of the proof that we can before the architecture is finalized, because at some point this will have to be built into silicon and then becomes too late to change it. So we attempt to make as much progress there as possible. So these are the plans for the next few months, I guess.
Okay, I think we should stop there. So thank you again. And if you could stop sharing and Stephen could start sharing.
Yes.
Okay, share. So are my slides now visible? And is the volume of my microphone okay, or do I have to adjust something?
The volume might be turned up a little too much. There's a bit of distortion.
Okay. Is that better?
Just about the same.
And now?
Yeah, that's better.
Okay.
If Lennart can start the recording. Yeah.
Done.
Then our next talk, Stephen Kuchel.
Yeah, so thanks for the introduction. So I'll be talking about our catamaran framework, which is actually a continuation of the theme of the previous talk. So we are interested in ISAs and specifically in security-related features. So I have to give a disclaimer. So this is actually a quite recent work, so we don't have research results per se. So this is a talk about work in progress and the current status. Okay, so yeah. So we see that security features are added basically into hardware to enforce isolation in hardware, and this can range from trusted execution environments, such for instance as trust zone over software compartmentalization, to really fine-grained memory protection, which is like offered by Cherry. Now, given formal ISA specs, we might even verify some of these properties. So architectural properties about security up to really machine-checked proofs of these properties. So this was the previous talk. So Thomas talked about a formalization of a security property for Cherry, but there's of course also other work on idealized extensions or smaller machine about security properties at the architectural level. So this is pretty cool and impressive, right? So I would actually grant you a secure padlock. So you, so I trust that there are at least some attack vectors which are closed. So I get some confidence into the security of my hardware. But what we actually want is kind of like the security of programs that are executing on the hardware. Security properties, and we want to prove these security properties either by reasoning or by actually getting them for free through the implementation of the program on the specific architecture it is run on. So then there's of course the question, how are these security properties at the program level related to the architectural properties? And there's a wealth of work in working on this transition to really see the connection and formalize these. So of course the devil is in the details. So for each of the things, you have to look at the fine print to see really what is proved, what assumptions are made, and what does it actually mean for my program. So we'll still be talking about the architectural level, so the lower level of this diagram. But we want to go towards, well, verifying the security properties on programs themselves. So we want to enable this transition to programs. So our work is going towards still verifying architectural properties, but actually pulling in machinery that has been developed higher level up. So specifically, we are interested in using recent developments in formulating capabilities for capability machines and object capabilities in higher level language, and using these properties and the machinery developed there to specify and prove architectural properties, with the goal then later they can actually be used to reason the programs themselves. Okay, so let's talk a bit about capabilities and capability safety for capability machines. So I'm going to assume a very simple view on a capability machine, where capability gives me authority to access a specific region of memory. So I've got a begin and an end address and the current cursor that points into that region, and permissions for what I can do to that region, if I can read or write to it. So the capability machine then gives me guarantees. So other adversary code cannot just forge capabilities or create capabilities out of thin air. So there are hardware checks that you can't actually meddle with existing capabilities or create them freely. The permissions when accessing memory through a capability have to be checked. And of course, if you manipulate a capability, say you want to restrict the bounds or something else, then, well, all the manipulations that you can possibly do to a capability have to be safe. So capability machines provide me these guarantees. Of course, these are informal, and you would still need to formalize them in some way. But the question is, can we actually verify that these hold in some way on the spec itself? Right. So as an example of an idealized capability machine, here's some code that executes a store. So where you want to store the contents of register S into the capability that is held in register D, and you want to store that into the memory cell that D points to. So what does this code do? Well, first reads the contents of the D register, and it reads a capability from it. Then it performs some checks. So it checks that the permissions of this capability actually allow me to write using this capability, and that the cursor within that capability is in the bounds defined by the capability. Then I assert here that these checks are actually true. So in a realistic specification, you would raise exception to transition to the operating system or something else. Then the code reads the contents of the S register, delegates the write to a lower level function that, for instance, can resolve virtual addresses to physical addresses or to some other computations, and writes the the red constants W, and then as a last step, increment the program counter to execute the next instruction in the next cycle. So these checks, so the within bounds checks and the write aloud checks, so these are critical checks, which are actually enforcing the authority of the capability. And I mean, this is a very a simple example, but of course the details are in the corner cases. So it's easy to overlook something, or if you have richer forms of capabilities, yeah, it's easy to just to have bugs in the corner cases, basically. So what we want to do is to apply reasoning techniques to actually ensure that these checks happen, and that they happen, that sufficient checks happen to guarantee safety properties of the architecture. So specifically, the kind of properties that we're interested in are, as I previously said, are recent developments in reasoning about capability safety in using object capabilities on programming languages or on capability machines. So specifically, the Toplas paper by Skorstengard and others defines a universal contract, basically, in separation logic that has to hold for each instruction of the architecture, and then each program that actually runs on the architecture will also satisfy a property that is encoded by this universal contract. So the universal contract that I want to give here to this execute story is that, well, okay, look at the contents of all the registers are, and I stipulate that what all these registers contain is actually safe. So, of course, there's a lot of detail and I can't go into it. So I just want to give you an intuition what this safe predicate actually means. So at any point in execution of your program, you can view actually an isolated memory subset that you are executing on. And more specifically for this memory subset, you might have you have registered invariants that have to hold. So some regions are only readable, some are read-writable, and so on. So the safe predicate then stipulates some closure properties on this memory subset. So if you've got a capability, then, well, of course, at least the region that this capability gives you access to has to be within the domain of the subset that you're looking at. And then furthermore, if you, for instance, have read permission to that to a specific region, then also all the values contained within that region have to be safe. And also for other kinds of permissions, similar closure properties have to hold. So now, given this this universal contract, we will of course want to check that this universal contract holds for our function. So by means of a program logic for the language, for the formal language that our architecture is specified in. So specifically, the program logic will allow us to reason about intermediate assertions that have to hold at each program point, and give us formal rules to establish the validity of this contract. And specifically, this contract also has to use contracts for other functions, for instance, like this lower level write mem function. Yeah. Of course, there's a lot of existing work on providing program logics for specifically for imperative languages. based on separation logic and having tools such as small footer verify very fast that read in programs and contracts, process these, potentially output verification conditions that still have to be checked in order to guarantee the validity of these contracts. So going even further, we have verified verifiers, for instance, such as the verified software toolchain that we heard about yesterday, or the Bedrock system, which are embedded in a general purpose proof of synthesis. And so in these two cases, it is COC, will also generate these verification conditions based on the program itself, plus the contracts, and verify the conditions using COC tactics or the automation that the proof assistant provides you. But furthermore, these are proved sound with respect to a semantics of the language itself. So this kind of summarizes what we want to do. So we want to develop a separation logic-based verifier for the sales specification language for ISAs, and also verify these verifier itself. So short overview of SAIL. So SAIL itself is a language and a tool, and there are multiple models written of instruction sets in the SAIL language. And the SAIL tool can then translate them into different outputs. So for emulation, for testing, for documentation itself. And what we are interested in is actually the output to proof assistants. So proof assistants such as Isabel, Hall4, or COC, for which SAIL already generates output. But we're actually developing kind of a new backend catamaran, which is also embedded in COC, which we haven't really integrated with SAIL yet. And so there's still kind of like open questions how we should really integrate it. But essentially, we want to output SAIL code in a different encoding in COC and use this then as the input for our verifier. So as I said, the catamaran backend, so I said 0%, we actually have not started working on this yet. So we have got a subset of SAIL we called micro SAIL embedded in COC itself. So in the future, we hope to like completely translate all SAIL models into a corresponding micro SAIL model. So the workflow of the verifier is then, so you get the generated micro SAIL model from the backend, and you have to provide more information about the contracts, basically. So you have to give a specification of predicates that you use in these contracts. You have to give the contracts of functions themselves of the ISA specification, and then further inputs, for instance, like lemmas to prove like difficult cases, or to establish properties of the predicates which are non-trivial, and then heuristics to apply these lemmas or to perform other kinds of automation. So all of these is plugged into the symbolic executor of Catamaran, which then also either fails or succeeds. And if it succeeds, it will still give you some conditions that you have to verify. So these are normally just pure verification conditions. So we aim to fully perform reasoning using spatial assertions, using the lemmas and heuristics And then the pure verification conditions can be handed off to Cog tactics, which then produce proofs of these verification conditions. So the structure of Catamaran itself, so it has multiple layers. So we have a symbolic executor, which automatically tries to apply or verify the contracts of functions. But to be actually, well, we also want to actually connect this to an operational semantics. So in between, we have a program logic interface, which defines an axiomatic program logic for the SAIL language, which includes a separation logic interface. So for these, we actually peek a lot at existing work. So for the program logic interface, we looked at what other people are doing in the verified software toolchain, specifically the MSL library within VST. We looked at Bedrock or Mirror Shard. So this also went into the design of our interface and at Iris. So in the future, we will probably look a bit more about what other people have done for automation. So our current symbolic executor is based on very fast, so which is one of the standalone tools that I mentioned previously. But so this is actually implemented as a symbolic executor within Cog instead of being a standalone tool. So these different parts of Catamaran then have to be connected. So at the lower level, we have to actually instantiate the program logic interface with a specific program logic instance, and prove that this program logic instance is sound with respect to the operational semantics. So we have got one very simple instance currently defined, which is just using disjoint heaps for registers and for memory. And we are almost about done with this with the soundness of this instance. Dilemmas that are being used by the symbolic executor and also something which we call external functions, they have to be proved sound with respect, well, either at the level of the program logic, specifically the separation logic, or even directly with respect to the specific instance that is being used. And then, well, the symbolic executor also has to be proved sound with respect to the program logic. So currently, this is still not yet done. So we're focused on the program logic soundness, but of course, there's there's still proofs left to be done there. So once you have established all of these soundness proofs and also the proofs of the verification condition, you can combine these and actually get a proof of a security property or another architectural property for your ISA. But as this is a work in progress, we have actually not verified a real ISA property yet. So regarding the supported features, as I said, we currently have a subset of SAIL embedded in Cog. So there are some features which we support and some features we support which the other backends don't. So for instance, I think the current proof assistant backends from SAIL actually completely elaborate mutable variables away, but we just added support because it was easy. In terms of reasoning about or implementing global states, as global state, we usually have registers and memory. So there's direct support for registers, but memory support, just like in SAIL, is actually not defined in the language itself. So we've got support for external functions, which are the only way to interact with memory. And then also in the future, we hope to be able to plug in, for instance, relaxed memory models by using external functions. At the level of the type system, so we support the primitive types, but also structured types like lists, records, and unions. So in contrast to the rest of the language, these are actually shallowly embedded, and only the constructor and destructor forms are deeply embedded into the syntax. And we support a kind of type polymorphism by actually reusing a form of template polymorphism. So there are some features which are not yet implemented. For instance, we have not yet worked on bit vectors, which are really needed if you want to go towards real world instruction set architectures instead of just looking at idealized ones. So SAIL supports static checking of bit vector lengths, but also supports different kinds of polymorphisms. So polymorphisms over integers, which are used to have well, dynamically sized bit vectors. So we're not quite sure how we should support these things. So we have a deep embedding, and we actually have a deeply typed embedding, and formally implementing these kinds of polymorphism would also require us to formally specify constraint entailment for everything that is available in a SAIL language. So instead of doing this, we will probably monomorphize these away, or even not statically check the lengths of big vectors, but in the type system itself, but then later on check these only in the logic. So there are some control flow constructs which we don't support yet. So don't really want to do while loops because we already have support for recursive functions, and we would rather just use that. But this is still open for debate. We haven't yet looked at support for non-local control flow via return or at exceptions, but these are very rarely used in ISA models. So we might also get away with not implementing, for instance, exceptions and elaborating returns in some form. There are other language features which, well, are nice for writing these models, but which are like immaterial for actually formally proving stuff about models. So the scattered definitions of SAIL, bidirectional mappings, for instance, between a AST definition of instructions and the binary encoding. These can just be elaborated, and support for assignments via complex L values is also something which we would rather elaborate away. So in terms of actually doing proofs, so there are some differences, some different design decisions that we did with the current backend that Sales has. So Sales backend currently produces shallowly embedded syntax in proof assistance over a monadic semantics. So a free prompt monad which encodes effectful steps such as reading or writing to memory or to registers. So whereas we chose a deeply embedded syntax in COG and provide an operational semantics for the language, of course, this choice then also affects the kind of proofs that you do. So the current backend, you basically do the proofs in the assertion logic of the prover itself, and use proof automation provided by the prover, such as the LTAG language or Eisbach. So whilst we, in order to support the reasoning, the kind of reasoning that we want to do, for instance, about capability safety or others, other properties, we work in a separation logic, so an embedded separation logic within the prover. And so we actually intend to provide proof automation via reflector proofs in Galena itself, rather than providing this on the level of proof tactics. So some future work. So this is pretty much work in progress, but short term, we want to finish some of the features of the framework itself. So we want to finish the soundness proofs of the program logic and also of the symbolic executor, and then go towards actually providing more automation and ultimately use this to and apply it to architectures itself. So initially, this will be on very simplified, idealized machines. So, for instance, a capability machine which can only hold registers, only hold capabilities and registers, which simplifies the construction of predicates somewhat. Specifically, the current program logic instance that we have should be sufficient to encode interesting properties for this machine. Then further scaling it up, still working mostly, I would say, on idealized machines. So there's recent work on linear capabilities and local capabilities, and a newer form of capabilities called uninitialized capabilities. So we think that for the linear capabilities, our current logic instance should also be sufficient. But then going on forward from there, we will probably need to switch to much richer separation logic in instance, and we potentially might reuse Iris as the lower level logic in our framework. Then, of course, want to go towards real-world systems, and from the language features, we should at least support bit vectors. So we might work on a memory safety property for a very simple instruction set architecture, which is called Redfin, that is used in satellites, which I mean, it's a real-world architecture already, but is sufficiently small to actually encode in our framework. And then further scaling up, so in the long-term future, well, we want to integrate our framework with SAIL, because we also want to work on the defined SAIL models themselves. And then there are multiple possibilities. So so one interesting thing would be to scale the property proofs that of idealized machines up to production scale machines like Cherry, or going more forward to actually look at different ways of connecting the security guarantees of programs and of security features of high-level languages to actually low-level implementations. So via, for instance, secure compilation. Okay, thanks for your attention. I'll take your questions.
Okay, thank you very much. We have already a whole line of questions. Martin Berger says, how much work would it be to scale up to full SAIL?
In terms of the language itself, I don't think that we're actually that far off. So it always depends on the kind of elaboration that would happen before actually outputting micro-SAIL code. In terms of all the other parts like proof automation and being able to handle large-scale models, that's still a lot of work, definitely.
Adam asks, I don't know if he thinks you've sufficiently answered, what made you choose a deep embedding of micro-SAIL as opposed to the Sail's own shallow embedding?
That's a very good question. So I think in the specific choices that we did differently, the important choice is the formalism of separation logic. I think we feel strongly about that. I don't specifically feel strongly about the deep versus shallow embedding. So, I mean, there are different trade-offs, but I don't think that there's like a very good thing that the deep embedding enables us to do that wouldn't also be possible in the shallow embedding, other than the proof automation via proof by reflection without actually reification of the shallowly embedded language.
Nico Broad-Santoni asks, is it a main goal to build a verified symbolic executor for arbitrary ISAs that have a sales spec, or is that, quotes, merely a byproduct of the project? They'd be interested in integrating with a multi-ISA symbolic execution engine.
So we're not specifically targeting certain ISAs or even certain properties, architectural properties. So the logic itself should be, well, general purpose to the extent that Sail is general purpose. So it's specifically tied to, still specifically tied to DSLs, to the ISA DSL of Sail, but it's not specifically tied to a specific ISA itself or the property.
I can add to that. So symbolic evaluation means a million things to a million people, but for a non-separation logic symbolic evaluator, one should look at Alistair Armstrong's Euler tooling that he described yesterday. Next question, Julia Belyakova says, at the beginning you showed the safe predicate. I missed whether it should be possible to prove such predicate automatically with Catamaran.
So the safe predicate, what Catamaran should prove is the usage of the safe predicate. So you still have to define that, build this basically yourself with respect to your memory instance. And what you also have to prove are lemmas about this. So you have to prove these manually, either, as I said, against the separation logic interface, or even against the specific instance of your program logic. What Catamaran then does is automatically apply the lemmas that you proved. But it's not giving you much help in actually defining these predicates, or even proving lemmas for these predicates.
Anjum Shlipala asks, are you saying you want your proof automation to be fully reflective? He hasn't seen any projects be successful yet without the chance to fall back to tactics for the harder verification conditions.
Yes, so this will probably be also the case for us. So as I said, we have got multiple possible ways in which the user of the system can interact with the symbolic execution. So via lemmas, via heuristics that are plugged into the symbolic executor itself. And then later on, of course, once we give up, we also produce verification conditions for the user. So one of the differences probably with other approaches is that, well, we're still working in a certain domain of ISAs. So also the theory that we need, I mean, we will we will need to reason a lot about bounds, about bit vectors themselves. So this is very specific to the application domain. But of course, we're not building a general purpose symbolic executor for a general purpose language.
Alex Copland asks, could this work, or perhaps SAIL more generally, be used to reason about the equivalence of small sequences of machine instructions, e.g. for checking the correctness of compiler optimizations?
Short answer, probably yes. I mean, so SAIL itself defines the semantics of instructions. So per se, there's, I mean, SAIL itself is not specific to proving architectural properties. So you can take the semantics of your architecture and basically also reason different ways about this, for instance, by simulation proofs for proving equivalence.
So if, I don't know if Alistair Armstrong is online and has working audio, but he might want to speak to whether EILA can be used for this.
Can you hear me?
Yeah.
So it should be, though in the context of a compiler, so you could take two sequences of assembly and show that they generate the same trace. That would be fine. In the context of a compiler optimization, the compiler is going to do things like remove memory accesses. So you need to figure out what you mean by equal in the context of compiler optimizations. But in general, I think so.
Yeah, so for some of the instruction selection optimizations that John Regier et al. Have been checking, I imagine EILA could be used to just test the equivalence if you wanted. Do we have any other questions? I have a question. So, and this affects how much of SAIL you want to cope with. How at what point and how seriously do you want to be able to cope with either the RISC-V or the ARM, full ARM spec, should we say? I mean, is that a main goal, or is that something that might or might not happen in the future?
So, I mean, using this as the main goal is kind of, I would say, very dangerous, because I mean, we are still a long way off from actually be able to tackle realistically sized ISAs with our proof automation. So I mean, I can't just work multiple years on one such specific goal. So we define intermediate milestones, like for instance these idealized capability machines. But I mean, being able to handle and being able to scale some of the properties up would definitely be in our interest. But the question is then, how much of a realistic machine can we actually cover, and what kind of assumptions do we really have to make then?
Yeah. Have you talked at all to Mark Wassel and looked at his mini-SAIL and mini-SAIL plus fragments of SAIL?
So we have looked at mini-SAIL itself, specifically at the very beginning when designing, and looked at the choices that were made there. So the goals are a bit differently. So one of the goals of mini-SAIL was also to formally specify the type system of SAIL and the type checking algorithm of SAIL. So mini-SAIL includes the lightweight dependent types that SAIL has, and is also has a bidirectional type system. So these were kind of like non-goals for us. So I mean, we would like to just use fully annotated SAIL programs where all overloadings are resolved, and just use this. So the type checking of SAIL itself is not a concern for us. So in terms of the language itself, we made some other choices. So we also have a stratification into statement and expressions, and so the choices we did there are a bit more geared towards the separation logic. I think one of the choices was that in Minisale, access to mutable variables is not an expression or something. So as I said, there are just, I mean, some choices that we did differently in the stratification.
Yeah, I mention it because he has some partial infrastructure for translating from Sale into these. So we might want to talk about that at some later point.
Yeah, yeah. So for actually elaborating Sale into microsale, so I mean, I know that there is this LEM intermediate language which is used in the Isabelle and Whole 4 backends, which also does not support, for instance, the lightweight dependent types that are used in Sale and that are, for instance, elaborated in the Coq backend. So, I mean, it would also be a possibility for us then, instead of going from full Sale to actually use the LEM output, or even some other output that is generated from Sale. So we would definitely like to reuse existing work instead of reinventing it.
Do we have any other questions? Not so far in the Slack. Then thank you again.
Yeah, thanks.
So now we have a pause until the turn of the hour, when Philippa Gardner and Conrad Watt will talk about Gillian and WebAssembly.
you must have managed to share your screen without me doing anything. All right. Look, are you there and can you hear me? I can hear somebody shouting. Is that you, Flipper?
Hello?
Aha. Hello, I can hear you.
Hello, Philippa.
Okay, good. So I don't know who's hearing me or not at the moment.
Probably everybody is hearing you.
Okay,
Everybody.
so
Probably.
I can't start video, but can I just do screen sharing?
Yes.
Okay, so I just do screen sharing and then we're done.
Yeah,
Okay.
it was 5 minutes ago. Now I don't see screen share currently.
No, I'll come back.
Yep.
So now I've screen shared.
Yeah.
You might want to share only the window instead of your whole screen.
Yeah.
Yes, but now you should be able to see my window is the whole screen, so you should see everything.
Yep.
Yeah. Yeah.
Yes, I'm now fine, right?
Yeah.
Phew.
Leonard and Peter, is there a way to have a speaker share video?
I can't hear that voice very well.
Okay, that's Ian.
Okay, I can hardly hear you.
I'm going to switch which microphone's on.
I can't hear Ian. I could hear Peter and Leonard.
Can you hear me now?
That's better, but it's very quiet.
Very faint. I'll try and
Oh,
fast it
much
up.
better. Whatever you did, do it.
I don't know. It's all like this. This is why we need a full half hour between each session. The Leonard and Peter, is it possible for the speaker to share video should they wish to do so?
I don't think I need it. I think I'm fine as I am.
I have a feeling the organizers could use the webpage of Zoom to change this setting, but maybe at this point we should just stick with the current scheme.
Yeah, I mean, I don't know whether this is an audience preference or a speaker preference.
I think it's a property of the webinar. It's a security feature.
Okay, that could be.
In that case, I'd be cautious trying to change things in a running webinar because certainly I can't stop the webinar and then restart it, I think. So,
Leonard, do you see a badge at the bottom of the screen? Looks like a shield and it says security.
You're using enhanced encryption, it says. Let me see.
I see that one at the top of the screen, but when I'm hosting, I usually see a button at the bottom, which lets you tweak things like can people use video or screen share, etc. But I've never run a webinar, so it might be different.
No, I just no, I don't see any of that. I could go to my settings, but in the setup, I'd be cautious editing the configuration page for the webinar because that might stop things.
I think we're fine as is.
Okay.
Yeah.
Has anybody seen the second speaker of this session today in the list of participants? I haven't heard from
We're expecting that Conrad will be on giving the talk, are we?
Yes.
Yeah, I'll ping him.
We're intentionally live streaming this exciting setup period.
Again, I'm not sure whether I can stop and start the live stream without killing the thing.
And I've heard that it changes the URL, which confuses everybody. So I see
I'm not recording at least, so.
Okay.
This, I think Zoom is experiencing some stress testing. Has been doing it for 3 months, I guess.
We're the ones being stress tested. Do I understand that Leonard exclusively turns the recording on and off?
Yes.
Right. So the way to enable it is to ask you. That sounds good.
Yeah. Yeah.
Hello. Can I help somehow? What's the problem?
I think we decided there is no problem. It's a little funny that we're live streaming us talking about setting up the session, but we can live with it. And it's a little funny that we don't have video of the speakers, but we can live with it.
You can activate video. 1 second. So there should be 3 dots, but only the host can see them. So Leonard in the panelist pane, to the right of mute all and unmute all, there should be 3 dots.
Yes, give me a second.
And there should be an option there to allow panelists to share their video.
Yes. Allow
Start their video.
Start video. Yes. Okay. Sorry.
And there was also a problem with sharing slides, or is there any other thing?
No, that's fine.
So I now turn that on. So Philippa, you should be able to switch on your video if you want.
But I don't need to, right? There's no.
Yep. Boom.
It's
There's
not going
no-
to change anything.
Well, people would be able to see you if it's on. I think it does go to
That's
YouTube.
that's what I was wondering. Oh,
So maybe
God.
you could test it if you don't mind, even if we decide it's not a good idea.
The idea of being seen is a bit weird.
It's working.
Hello.
Hello. I remember even hearing you on the LDR sound. Being seen shouldn't be that weird.
This seems very odd. We've just not been seeing anyone. So I'm going to just try screen sharing again, and you're going to tell me what is working better. I don't mind.
Yep.
Okay.
Okay.
Okay, and we then get a choice whether we can see just you and the slides, or anybody who's got video and their slides, which would normally just be you. Unless you want to demand to see an audience, that might be.
The way it usually works is that the video frame switches to whoever made a sound most recently. So if everyone else mutes, then we can maintain the invariant of seeing only the speaker. But it also is it's a pretty good heuristic for when another team member jumps in to answer a question.
Guys, you make the decision on or off.
On. I think having speakers good.
Okay.
But we will need to see whether, I don't know whether it comes through on the YouTube one, possibly not. Oh, it does, yes. So on YouTube, you are, or the speaker is in the corner.
Yeah, the most recent speaking person is in the corner until they stop speaking, and then no one's in the corner.
Okay, so this works.
Yeah, I think that's positively useful.
So I've got me, Ian, Peter. Peter's just gone, and a few others I presumably switched off.
Yes, I think there should be a distinction between speaker view and gallery view somewhere, where speaker view sees just the latest speaker and you can pin people, and gallery is a bunch of whoever talked recently.
I'm just going to leave it as it is. I'm not going to try and do any more. Yes, I am. Let me just say. What does that do?
So we can now see you live streaming yourself.
Okay, so speaker and gallery doesn't change anything from my point of view. I see, it's not making a difference. But what is making a difference is that that's fine. Good. Okay.
Oh, and I have an important question, which is it a hard G or a soft G in Gillian?
It's Gillian. As in Gillian Anderson.
All right, fair enough. Right, we're at 3 o'clock, so welcome back to the REMS DeepSpec workshop.
Wait, let me just start the recording.
Oh, yes, so Leonard, if you could start recording. That's great, thanks. Welcome everyone back to the REMS-DeepSpec workshop. The first speaker of this session is Philippa Gardner, talking about Gillian, multi-language platform for symbolic testing and verification. Gillian, sorry, Philippa.
So hello everybody, we've just doing an experiment about video. I don't quite know why I ended up the guinea pig, but this is what we're doing. And actually I had quite a bit of nostalgia yesterday. So whether it would be old friends or new friends, I'd hoped to show people my favourite haunts around London. And I'm afraid this can't happen, but I think this online workshop has been absolutely fantastic. And big thank you to Peter and Leonard for organising it, and for Ali and Amina for organising the whole PLDI conference. It's amazing what's happening, and I don't know about you, I found the talks really good so far, so I'm very much enjoying this. I'm going to talk to you today about Gillian, a multi-language platform for symbolic testing and verification. And here are my co-authors. There's Jose Fragoso Santos, who used to be at Imperial, but has just got an academic job at the Technical University in Lisbon. And he's had a baptism of fire because he's teaching a huge class for the first time online. And he's just about survived this term. There's Petr Maximovic, who is a senior research fellow in my group, and Sasha Eli Anois, who is a PhD student. So here are some highlights of verified software done at Imperial as part of the REMS project. Actually, this lot wasn't REMS, but most of it was REMS. And we've done some work on modern concurrent separation logics, where the idea was to build up abstractions to get to a level of interface where the specification is such that you can prove implementations correct with respect to the specification, and have approved properties of client programs using the specifications of certain functions. So we started with the CAP logic, which was done with some people in Cambridge before REMS. And there we put logical abstraction into the heart of the modern concurrent separation logics. Here we did logical atomicity, and here we're on the way to doing logical environment liveness conditions. And then right at the end, we've done some work on distributed atomic transactions. I now really understand weak consistency models, but it took me right to the end of REMS to produce some work on it. And given that people in REMS are at the heart of the beast doing weak memory, I found a tiny bit disappointed that I didn't get there a bit earlier. But basically my aim was to link the program logics from the strong concurrency world to the weak world. And what I found was that I couldn't do it without first doing an operational semantics. So this is just on operational semantics with a view to linking to the program logics in future. This CAP work also had another effect, which I'm not sure whether it was for the first time, but certainly we were doing it from the start, talked about negative resource. And in particular, given a set, you own the fact that an element is not in the set. And it started here for us at least, but then soon went to this place, which is a featherweight reasoning about JavaScript. A featherweight JavaScript. And in particular, the negative resource was really important here because the JavaScript programming language doesn't satisfy the frame properties, but with the negative information, it does. We did some work on mechanized specification of JavaScript in COC with some INRIA colleagues. And from this point onwards, I'm in huge land. So as my background, I'm much more in the featherweight place. And I actually found it very interesting being in this large world. And because of this world, I was able to do program reasoning about the JavaScript language in a huge sense. And it was because of this mechanized specification where we really got to understand the standard. So what we did here was full verification for JavaScript. What we did here was symbolic testing for JavaScript. And what we found was that we could unify the two via a common symbolic execution engine, which is what we did there. We've done some work pushing this out to events, but what I want to talk to you about today is our new work on Jillian. And whereas this other work is on the specific programming language JavaScript, now we're in this multi-language place, not wanting to just concentrate on one language, but to be able to work with many languages. So Jillian is this multi-language platform for unified symbolic analysis. We can do whole program symbolic testing using a symbolic execution engine, where the idea is that the developer puts in first order assertions about symbolic inputs and outputs and creates symbolic tests with these assertions. And either you get a correctness result given by bounded correctness guarantee, or you find a mistake and you end up with a counter model, concrete counter model, telling you what has gone wrong. With full verification, the difficult bit is the developer needs to talk about and reason about abstraction. And we've got specifications in separation logic, invariance, lemmas, and tactics. And all of this has to be understood in order to work with the language that you're wanting. And we end up with functional correctness guarantees. And if we can't get those guarantees, we end up with a symbolic trace that's failing, and we have to really understand why. This world is difficult. It needs a real specialist developer to understand what's going on here. And then finally, we've done compositional testing using biabduction. And there, the point is that the developer does very little. Maybe some lightweight type annotations to annotate what's going on. And either you end up with boundless correct specifications, or you end up with lightweight bug specifications. Of course, there's a trade-off between these various approaches. This one is hard because you're giving no help because you've got very little annotation. So for the Jillian platform, excuse me, I'm just trying to get rid of the photos because they're in my way. So for the Jillian platform, the basic infrastructure is that we compile from the target language to an intermediate language. Now, this sort of technique has been done for a while. We have a little bit of a difference in that we're aiming for many languages, not just the one language or a menu of languages. So for us, we have got a platform where the idea is that a tool developer can use our platform to create a tool for their favorite target language. And in order to do this, we are parametric on the memory model of the target language. So we develop an intermediate go-to language, Jill, parametric in this memory model. It links to a first-order solver powered by the Z3 theorem prover. And we do a modular analysis. We have core symbolic execution engine. And on top of that, we put abstraction and biabduction in a modular fashion. And this is what I'm going to tell you about today of how to do this. So what the tool developer needs to input is it needs information about both the concrete and the symbolic memory models of the target language. And in particular, we use the concrete target language memory model in order that we can get proper testing going on and to feel confident that what we're doing is correct before we build up the symbolic memory model. We also need a compiler from the target language to GIL. In our case, we're choosing to be really picky. We want our compiler to be really good and trusted. We want it to preserve the memory model, and we want it to preserve the semantics. Basically, the compilation step is just taking the control flow of the target language and rejigging it to the control flow of the go-to language without loss of information, preserving the memory model as we go. This is a very strong requirement by us, and other people that are using our tool needn't be quite so picky. And one thing that was really important for us, we wanted to understand which bits of the theory really could hook properly with the tool. We know that reasoning about trustworthy compilers is really hard, and we've got really good examples where that has been done. But also, at this tiny GIL intermediate language, it's only a little go-to language. So we can write down exactly what it says, and we can relate that to the implementation. And we wanted to do this right the way through, understanding which bits we could formalize and prove properties about, and which bits were not our job. It was somebody else's job to do so. So here is this formal semantics, and I'm not going to go through it. For those of you who know how to do formal semantics for go-to languages, there's not much surprising here. But we do need user input from the tool developer, giving basic actions for how to manipulate the memory. And it's the fundamental interactions between the language and its memory. And I'll show you how it works with a tiny little go-to language, tiny little while language, excuse me. So what's nice about Gillian, you can work with tiny languages and also work with real world languages. So especially given my spirit, I very much like working with a tiny language, such as a while, with as complicated memory model as you like. There's no reason not to work with complicated memory models. But here we've got a simple one, which is a static object property memory model, where we got concrete memory given by locations, strings representing fields or properties, and values. We also have symbolic memory, which in this case is very similar, but often isn't, where we've got symbolic expressions for the locations. We've got concrete strings for the fields, because here we're in the static objects, so we can work in the concrete place. And we have, if we were in extensible objects, we would have a symbolic expression here, such as for JavaScript. And we have symbolic expressions for values. Then we automatically lift this memory model to the states of Gillian. The states of Gillian in the concrete case, we have a variable store, and we do allocation once and for all because it's quite basic and we can get it in a general way. For the symbolic case, we have the symbolic memory model, a symbolic store with symbolic values. We've got symbolic allocation, and we also have a path condition, which is a small first order assertion giving information about which path you've taken, relating this information about the symbolic variables. We have basic actions for manipulating the memory, and we have a straightforward compiler from the while language to GIL. Here's the basic actions of the while language. We've got allocation, which we're not dealing with because we've done it once and for all in Gillian. And we have lookup, mutate, and dispose that we do have to deal with. So here are the action rules for lookup. If we have a concrete lookup of a concrete location and a concrete field, Then you find it in the memory when it exists and give back information saying it's a success state, it's a success result, and we've got the value. We could end up with an error because the particular location with the particular field doesn't have a representation in the memory. And in this case, we end up with an error and an error description explaining what's going on. And what's going on in this particular case is it's resource information. For those of you who know about separation logic, absolutely, I'm putting hints in here. And we've got a location and the field information that we're going to record. We've also got the symbolic lookup. And in particular, here we've got the symbolic location given by a symbolic expression. We've got the concrete field. We look it up in the memory. And what that means is, given the particular path condition we're at, if we can find a way of linking this E hat with this E hat prime, hats are meaning symbolic, that's how I use it. So basically, if we can say that these are equal in the context of the path condition, what does that mean? It means equal in the sense that we can hook it off to the Z3 theorem prover and say it's equal. Then afterwards, if we've got a success, we record its symbolic value and we record the extra bit of the path condition, i.e. this extra bit of information. So we're now with the path condition consisting of this and this extra bit. And here we're in a non-deterministic place because there's many ways of matching this E hat and P to the memory. So we're going to be branching at this point. We also have an error case where we can't find a match between here and the memory. And what happens with compilation to these actions, if we have this command in the tiny language, wire language we're using, then it gets compiled like this. We've got the lookup action with the appropriate arguments, and we record the value. And we have, for this value, we either have success or failure, and that's to do with the outcome of this action. And that this is given by the first projection, given by the 0th case. And the actual result we get by the second projection, this 1, which either returns the value or gives an error description. If we have an error, we record the failed case. If we have a success, we record the return value. And these are different outcomes. So we have a failure outcome and we have a success outcome, either giving the error description or giving the return value. So that was symbolic execution, and these little tiny actions are the things that the tool developer needs to give to the tool. Now, when we add verification on top using abstraction, the tool developer has to add these core predicates. So basically, these core predicates are tiny little assertions describing the memory building blocks. In the case of while, we have the normal heap assertion of separation logic corresponding to the heap cell in the underlying memory. And we have getter and setter functions for each core predicate. And let me explain what is happening by these. So in the case of while, we just have the core predicates looking like this, where here we have a symbolic location, a concrete field, and symbolic value. And we have the getter for here, which has the input information given by the symbolic location and the concrete field. And if it can find a match with the symbolic memory, match in the sense that these two are equal with respect to the path condition pi, then we take off this bit of the symbolic memory. It's like we're taking off this bit, leaving u prime, whoops, leaving the mu hat prime, which is the framed bit. So we've taken off this bit and we've returned the relevant information, which is the value of this that gets used somewhere else in a successful way, and ended up with the addition to the path condition given by that equality. We also have the setter, and for the setter, we give the information back. And what happens, we know that in the mu we're talking about, we can't get a match between the symbolic location and the field and the memory, because if we look here, we've got rid of it. So absolutely, we haven't got that match in the context of the pi, which is asking for E hat equaling E prime. So we're allowed to put it on and frame it on to the memory we have and get this bigger symbolic memory back. So this is how the getters and setters work for these core predicates. We end up with 4 additional rules. So here we've got the main core symbolic engine. And here we've got 4 additional rules for abstraction. The first rule just lifts what we have here to the abstract place. The second and third rule just deal with unfold and folding of user-defined predicates such as list, which I'm not talking about here. For Gillian, a lot of this is done automatically, but every now and again, the developer will have to give a nudge to the tool. And we have another rule for incorporating function summaries into, and in particular, the function specifications into this world. Finally, we've got by abduction. So we've given abstraction. Abstraction needed the core predicates. And now with by abduction, we need fixes of resource errors. So in particular, this is the first time that I'm giving you a rule. And I'm hoping that I'm going to be able to walk through one rule. So basically, if you're not familiar with the go-to world, this gobbledygook basically gives you enough information. You can find the next command that you're dealing with. Here it is. This alpha is an action. It's applied to its argument, and whatever value is it's going to get, it's going to return it and give it to X if it can. So what we do here is evaluate this argument expression to get the next state and its value. And now with this actually can be simplified. This state, we can think of it as not side effecting. We've got the general one here. So in this context, we have the action applied to its value, and we end up getting an error. So given this error, normally with symbolic execution, it would just stop. But now we can fix, and this is what by abduction is doing. And the fix is to add an assertion Q. In particular, the fix for lookup is if we have an error that's labeled by resource for resource error, and we've got the symbolic location and its concrete field, then the fix is to give this tiny little assertion, which is this core predicate, and we give it the value, which is a fresh symbolic value. Given this assertion, we set it to the memory. And now we actually do the action on the memory that actually really now can be done. Remember before here it couldn't be done, but now we've got more resource given by Q, it can be done, and we get the result. And that's our by abduction, we keep going. So I've briefly talked to you about how to get symbolic execution, the core engine, then build abstraction for full verification, then build up by abduction to get the automatic compositional testing. We've got general correctness results. They're stated and proven independently of the underlying memory model. And we've got minimal proof effort for the tool development for the user, in the sense that if they so care this much, we care very much, we can prove the correctness of our result, of the instantiation, by working with the actions. For symbolic execution, we have the correctness of the symbolic actions with respect to the concrete actions, for example, the normal, soundness, and completeness style results. For abstraction, we have a frame property for actions, and for by abduction, after we have an action fix, the execution can continue and can continue well. And actually, I'm not going to talk any more about these results, because I'm going to leave it to Petter's talk on Friday, because a lot of this work on symbolic execution has been, is going to be published in PLDI this time round. And in particular, something I'm loving is that we've got correctness results with a forwards and backwards feel. Forwards feel in the sense that we've got normal consequence, backwards feel in the sense we've got backwards consequence, in the style, I think, of the correctness logic of Peter O'Hearn. So what's going on, we believe, is that we've got a precise symbolic execution engine that can go either to verification in an over-approximating way, or to symbolic testing where, for example, we cut away paths. We can cut away paths with our work and get to an under-approximating place. And I think Pete O'Hearn might have really clarified for us what we're doing, but we've got to do more work to fully understand that. Petter will absolutely be getting to some of this in the PLDI talk. In the last so what I want to talk about is real-world instantiations. And we've done two. We've done C and JavaScript. We purposely chose JavaScript because we had such a lot of work that we'd done already. C for us is very new, but in particular, we very much wanted to work with two languages where memory models were so very different from each other, so that we could start understanding the resonances of the differences and similarities between the Gillian instantiations. So for C, we're basically doing CompSert. We've got a block offset memory model, which consists of a heap and permission table. We use the concrete memory model from CompSert, and CompSert has worked with the symbolic memory model, and we've had to adapt it a bit, and that's what we've done. Interestingly, there was very few actions. So for a real-world language, there are not many actions that are interacting with this the basic memory models. In the case of C, it's 16. They are quite simple. They are there for the management of the global environment, the heap, and the permission table. So this is giving us a bit of confidence that we haven't done it yet. We've explored a couple of cases, but we should be able to write down all cases and prove our parametric correctness results for this instantiation. I didn't say that very well. We've got our parametric correctness results. We need to instantiate them to C. And we do this by working with these 16 actions and proving little lemmas about those 16 actions. Our compiler to GIL is CompSert. We go to C# minor, and then we go from C# minor to GIL. That's almost the identity. Of course, it'll be very easy for us to verify this tiny bit of extra compilation to GIL to get it all verified in COC. And that's something that actually we want to do, and we want to work with COC quite a bit in this project. We've got Gillian evaluation, both for the symbolic testing, the verification, and the biobduction. In the symbolic testing, we are working here with very tiny data structures. And in particular, let's look at key value map. It's implemented as a singly linked list. And what we need to do for tests is provide first order assumptions and assertions on symbolic inputs as part of the code of the tests. Here's the declaration of symbolic inputs. We are asserting that if we have an empty map, we put in a key value pair. It only has one node. We've not got on to the next. We've got no extra nodes in our list, and we get back the key, the value of the key. We should end up with the same value as we have before. And in this case, we do. We have specifications that require abstractions at the level of developer. And this is really, we work really, really hard to get these specifications right. So there's a lot of work under the hood, but we can end up with abstractions where the get function, when it's getting the value of the key k at map m, it has the key value map at address m, which has this set of key value pairs, including this pair. Then what you do, you return the appropriate value. The developer can understand that, never mind how difficult it is to build up abstractions in separation logic. So the automatic specifications given by biobduction, they require no annotations, but the specifications look like this. So here we've got the case where we're looking for the key k. We get a k key prime, which is equal to k. We're in the case where we're just looking for the map with one node, so we're only looking at the one node case, and we return the appropriate value, or we return the null case because actually the k prime doesn't relate to k. And this is done automatically, and we're actually having quite promising times. This notation here just means we're artificially putting in some errors to see if we can get at the errors. So these are the error cases, and these are the successful cases that we then fix and are then successful. But all of this is very toy. This is just setting the scene for us, making sure we're working, giving simple implementations. We have collection C library that is not toy. It is small, it is standalone, it is this sort of order of size, and it's active on GitHub. When we think about it in this world, for symbolic testing, we have this level of executed GIL commands. So it's getting bigger compared with what we were doing here. We've discovered bugs in the libraries and tests, and in particular, here what happened, we got over allocation. We were allocating 100 cells instead of 10, something like that. And the way it happened, we found this by doing a symbolic test, and then we looked at the memory trace because something odd was happening. So we didn't directly find this from the test, we found this from the memory trace. And we actually think with these symbolic tests, we should be doing much more. We should be really simplifying and systematically thinking about these symbolic tests, because I think they're just so much easier to use than unit tests. And why aren't people using them? Well, as a community, what's it mean to get from the unit test to the symbolic test? All bugs were reported and fixed. In progress, we're doing verification of parts of collection C, and this is really interesting to us because what we found was that the memory model that we first thought of, the symbolic memory model, doesn't work for collection C. And we have to be more subtle with the memory model, and we can be, and now we're doing that and doing rather sophisticated, quite sophisticated verification here. It's taking us a long time. It's quite hard because verification of real world code is not done very much yet. We're still on a learning curve with that. And that's needed before we get to the biobduction, because we need to understand our memory model well. So given that we need to understand our memory model well, we're doing that before going to the biobduction. That actually looks promising for C. We need, so now we do real world instantiation for JavaScript. This one is way more mature because we've been working with JavaScript for many years. So now the memory model is different. We've got an extensible object memory model. This has all been inherited from JavaScript. We only have 8 actions and they're simple. So again, we're going to be able to prove our little lemmas. And we've got the compiler that we developed, trusted compiler from JavaScript to an intermediate representation that now goes to Jill. And there we set up the methodology that I think is well known by now, that we follow the standard line by line, we preserve the memory model, we test well. We have a bonus that we've added to this work now. We do JavaScript events. And in particular, we work with DOM events, JavaScript promises, and a way to sync, all starting off with a module of general events for Gillian. Here's the evaluation, first in the small. We've got a key value map implemented as an extensible object, and now we are not 100% safe. The reason for it, given what one would expect to do for the implementation. And the reason is given by this, captured by this test here. It's the same test, you get what you put using first order assumptions and assertions on symbolic inputs, and basically you get a mistake. And for those of you who know, because we've got extensible objects, we have something called has-own property for finding the property or the field, because it's we don't know what fields are in these extensible objects. So has-own property is a function. It's a function that's necessary for the get method. And if we have a key that happens to be called has-own property, we'll be in real trouble. And so we can find it using this symbolic test. We also have specifications that are looking very like what's happening to C. The difference is to do with map proto, and again, for those of you who know JavaScript, it's all about the proto chains. And in particular, this is a particular map object, whereas here we have general map proto, where you find the get function and the put function. And so we need to make this explicit. The specifications of JavaScript are way harder than for C because the abstractions are more complex. We've done some work with Amazon. There's a developer that looks at English descriptions, comments about the code. We're changing those English descriptions and turning them into formal descriptions using our Gillian work. First Javert, now Gillian. And we discovered he hadn't got the has-own property, and of course it wouldn't come up very much, but it was nice to find. But actually something we found very interesting, it improved the implementation, because he'd done some shortcuts which didn't follow the underlying data structures. And if you're doing verification, you have to follow the underlying data structures. And he liked the fact that we were making suggestions that made his code better, and he judged that it did make the code better. And so he was pleased to change his work, which we liked. We can find the has-own property bug using biobduction, but the times are way slower than in the C world. And this is because JavaScript semantics has so many paths to the standard. We have to do a lot of work to understand what biobduction for JavaScript is. We've done real-world code. We found and discovered bugs. And here we've been very systematic with our symbolic tests. And basically an MSc student who was an intern did this job really well without understanding Javert at the time. So we do think going from unit tests to symbolic tests is not unreasonable. I don't have time to go through the JavaScript events work, just to do the highlights, which is we looked at the cache library, which is a compact alternative for jQuery. In particular, it's working with DOM events. We're now at the level of 4 million executed GIL commands. And we can do boundless correctness guarantees. If a single handler has been registered to a given event, if the event is at most 20 characters, then it's only the handler that can be triggered for that event. That actually didn't hold. We found the bugs and then proved this property. This is our eCoop paper. So just in summary, we have a platform for unified symbolic analysis called Gillian. We can do whole program symbolic testing, full verification, and automatic compositional using by abduction. We've got a toy instantiations such as Wire, 2 big real-world instantiations. Would love to do more. In particular, Sasha really doesn't want to work with C. He's been wanting to work with Rust because it's modern, up to date. And then he heard this wonderful Caven talk yesterday and went, I have to do C with Cerberus. So I don't know what will happen. We will talk to Cambridge guys and we don't know, how busy they are and what have you, but we would love to convert our work to Cerberus. And we actually have somebody enthused right this second. Let's hope we can do it. We've also separately done some work on mechanized specification of WebAssembly using COC. Conrad will talk about it in the next talk. So we've got this expertise about WebAssembly and it makes sense to push it to Gillian. I would love to work with domain-specific languages because it's the medium place between the toy stuff and the huge real-world stuff, but I don't have much to say there. We've got, of course, we've got things to improve. We've got an MSc students just finishing doing error reporting and continuous integration. And then we've got to do a lot more on the analysis. So just in summary, for REMS, I've worked on concurrency, I've worked on JavaScript, in particular work on DOM fed into the work on JavaScript that I'd done in the past. And now here we are on Gillian, this multi-language platform for symbolic reasoning. And what I absolutely would love to do next, I want to change the JavaScript events to Gillian events. We should be able to do WebAssembly events given what we've done. And so that's something we want to do. Also, I want to hook up Gillian to concurrency, very much hooking up my concurrency world to the Gillian world. This will be very simple at the start. And I think something that's absolutely begging to be done is Cox certification. We are so close linking the theory and the implementation. We should take it out, do all this work in COC, do the generalized parametric correctness results in COC, so you only have little lemmas for the instantiations. That's the tiny piece of work. Then what does it mean to do the big piece of work where you can get a real proof term for our analysis tools that can be then properly certified in COC? I would love to do that. I actually have funding to do that, and if anyone's interested from this amazing COC community that wants to do something like that, we would love that. Petter's a half expert. No, I shouldn't say that. Petter's a real expert on COC. He just hasn't done it for a while. So we've actually got quite a bit of expertise at the moment, and we would love somebody to hook into that work. Thank you very much for your patience and listening.
That's great. Thanks, Philippa. We have 3 minutes for questions, and I can see there's a few on Slack already. So from Yulia Belyakova, could you elaborate in which ways the C model turned out to be too simple for collections?
So it wasn't too simple for collections in the case of symbolic testing. But in the case of verification, there's two things needed to happen. One is, I believe, and others will know about this better, but I believe that we needed more fine-grained reasoning, just because you're really having to pull things apart in a way that the symbolic testing is very much on the whole. And also, we needed to change the instantiation of Gillian a bit to get a better link between the symbolic memory and the core predicates. We just have to work harder than we've done in order to pull things apart more.
Okay. There's also a question
what's
from...
so interesting, what it's going to mean is a more fine-grainedness of the memory model, and the symbolic memory model is just going to end up different from the concrete one. So it's not just a lifting of the concrete to the symbolic. There's real differences going on, and this is, we haven't done the, we're on the way to the work, so we haven't published the work yet.
There's a question from Matt Windsor. Saying this feels very similar to your work on the views framework, especially with the user parameterized separation logic. Is there a substantive connection between the two? And does the work on Gillian spark off further directions over unified bases for concurrent programming logics?
I don't fully know the answer to that. The views work, it was one route that turned into that large IRIS project. And I'm always thinking, what does it mean to hook this work onto the IRIS project? And I'm not there yet. What I do think is that we've got a nice way of thinking about memory, these parameterized memory models, and I would love to understand what it meant to hook that into the IRIS work. Also separately, it's being led by Alan Schmidt in INRIA. We're doing work on, we've done some work on skeletons of what does it mean to think about a general way of thinking about proof rules for, not proof rules, rules in an operational semantics, and how does one think about operational semantics in a generalized way? And we're really wondering how all this hooks together. And I know the sort of Otlem work of Pete Sewell and others, we're in a different place from that. But somehow this Gillian work, this IRIS work, and in my past, the views work, and the how does one think generally about the meta description of operational semantics. I'm really trying to hook it all together, but there's a long way to go before we're anywhere near.
Okay, thanks. There's one further question on the thread, on the Slack thread, but it's all from Adam Klipala about potential clashes in the symbolic state. But Jose Santos has given extensive answers there. So unless Adam speaks up, I'm going to say that's the place to have that discussion.
Thank you, Jose.
The answer broadly seems to be it's all fine. But
that is the answer.
Okay, thanks so much, Philippa. We have our next talk from Conrad in a couple of minutes. And so, yes, Philippa, if you could stop sharing your screen, we can start sharing up the next set. Thanks very much. Okay, Conrad, you should be able to share your screen or application as you choose.
Let me know again when you want me to start the recording.
Yes, thanks, Leonard. So Conrad, we can see you, which is good.
I will need to restart my Zoom in order to share the screen, unfortunately, so I'll just be back in a second.
Okay, see you soon.
hello, can you hear me?
Yes, I can hear you and see you fine. Are you
Right.
now in a position to share your screen?
Yes, I believe so.
That looks good. We can see your screen and a full screen set of slides there.
All right, is that good?
Yes, we can see that. And also your cursor when you move it, if that's useful for you.
Yes, that is. Okay, perfect.
Great. Okay, thanks. So, Leonard, could you start recording, please?
Yep.
Great. So, welcome back to session 5 of the REMS DeepSpec workshop. We now have a talk by Conrad Watt on WebAssembly, sequential concurrent semantics. And there are questions asked on the Slack channel. I'll put the link in the chat on Zoom. Thanks very much. Conrad.
So, hi, I'm Conrad, and I'm here today to talk about my work in collaboration with a lot of other people into researching the WebAssembly programming language. So, excuse me. So to understand what WebAssembly is and why it exists, we first have to understand JavaScript. And Philippa has been talking about JavaScript already and giving you a sense of how complicated and weird this is. But JavaScript really was kind of prototyped in a hurry many years ago, almost 25 years ago now. And through an accident of politics, it is pretty much the only language you can build a website with. So a lot of people rely on it. And this is a bit unfortunate because when JavaScript was designed, the web was very simple. And this is just a screenshot of a very simple website. It's got text, it's got basic HTML. And it's actually my supervisor's website as it exists today. So maybe for some people, the web still looks like this. But actually, in general, people are pushing the bounds of what can be expected from a website. We're building in richer computation that can be expected to run in a web browser. So here's just an example I plucked off the internet. If you visit this web page, then it will load up a real-time 3D simulation of this cube of water, and you can drag your mouse cursor around to create ripples in it. And all of the calculations for that actually have to be done in JavaScript, which is kind of unfortunate because JavaScript is this very high-level scripting language. And recognizing that people actually are looking for a new way to do more efficient computation on the web, representatives from pretty much every major web browser tech company got together and decided that they needed to design something new. And that is WebAssembly. So WebAssembly is actually kind of this political miracle because it's very hard to get these companies to agree on anything. And the vision for WebAssembly is that, like JavaScript, it will be ubiquitously supported. It is ubiquitously supported across the web now. It is actually in all web browsers. And you can take a program written in a low-level language like C or Rust, compile it to WebAssembly, and then run that in the browser to get near-native performance. And the exciting thing for us is that WebAssembly is in fact fully formally specified and was designed that way from the beginning. So just as a kind of a depiction of how WebAssembly might be used in the real world, starting from right to left, you have a producer who has a C program that they're going to compile into WebAssembly. And they might use this program on their own website, or they might put it in some package management system like NPM. And then the web developer will stitch together WebAssembly and JavaScript and HTML to make their website. And then a web user will visit the website, and then they will download all of this WebAssembly code, and their web browser will compile and run it on their local machine. So where do I come into this? Well, I've been working very closely with WebAssembly's standards body, particularly on developing WebAssembly's relaxed memory model for its threads extension. And I've also been doing a little more kind of blue sky research into hypothetical language extensions and program logic work. And I have found sometimes that there is a tension between producing novel and kind of interesting and publishable research and producing something that is palatable to the industrial side of WebAssembly. So later on in the talk, I hope to give you a couple of examples of that. So at a high level, I'm first going to be talking about WebAssembly's formal structure as it's defined in the official specification, with the aim that you can come to this talk and then go away and read the WebAssembly specification and not be too surprised by what you find there. And then I'm going to be talking about my mechanization of that formalism and some issues I found and some properties I proved. And then moving on to some security properties of WebAssembly and some hypothetical extensions to do with that. And then finally, my work with the group on WebAssembly's relaxed memory model. Okay, so at a high level, WebAssembly is a stack-based language. It's specified using a formal small step semantics. And in addition to this, every WebAssembly program has to be type checked through a validation procedure before it's allowed to run, and only well-typed programs are allowed to be compiled and executed. So at the bottom here, I'm just depicting a very simple WebAssembly code fragment executing, and I'm only using 2 WebAssembly instructions. First, I have this type annotated const instruction, which pushes a single value onto the stack. And then I have this add instruction, which will pop 2 values of the appropriate type off the stack and then push back the result. So here you can see the execution just proceeds exactly as you'd expect. 2 values are pushed onto the stack, and then add will pop them off and push back the result. So WebAssembly's type system is based on describing the way in which program fragments transform this value stack. So the structure of a type is a list of types to another list of types. And these T's are the fundamental WebAssembly value types. And you can either have I32 for 32-bit integers, I64 for 64-bit integers, F32 for 32-bit floats, and F64 for 64-bit floats. And every WebAssembly value will be one of these 4 fundamental types. So for example, a const instruction just pushes one thing of the appropriate type onto the stack. So its type can be described as, if you start with an empty stack, you'll end up with one thing of the appropriate type. Similarly with add, you require 2 things to be on the stack, you will pop them and then push back the result. So you go from 2 things on the stack to 1 thing being on the stack. And then with this program fragment, you start with an empty stack, you push 2 things on, you pop 2 things off, and then you push back the final value. So this is the full type. And then here we have a type error in this 4th example, because first I push a float onto the stack, then I push an integer, and then I try and do integer addition. So the WebAssembly type system will catch this, and this program will not be allowed to compile or execute. And obviously, because we're dealing with transformations of stacks, you also need some weakening rules. The type of a const instruction, for example, is not just an empty stack to 1 thing. If you start from a stack with 2 things on it, then you'll go to a stack with 3 things on it. So these are just some structural rules that allow you to weaken and compose types in that fashion. So the core of WebAssembly's reduction rules, its dynamic semantics, is this small step execution relation. And it describes an execution going from configuration to configuration. So this is kind of the core of WebAssembly's state. And a WebAssembly configuration is made up of 3 components. First, you have the global store, which collects all of the globally allocated state of a WebAssembly program and between all the programs that are currently running in the system. You have F, the function local frame, which describes all of the scoping information that's relevant to the current function being executed. And then finally, you have the code itself being executed, a list of expressions. So here is just a very simple kind of a fragment of WebAssembly's AST and 2 reduction rules as you can find them in the WebAssembly specification. I'm just talking about 2 instructions right now, the ones you've seen before, the const instruction, which pushes 1 thing onto the value stack, and the binary operation kind of family of instructions. Add is one example of this, but you also have multiplication and division and others. And all of these come with an explicit type annotation. So here's the reduction rule for binary operations. And you'll notice that the value explicitly represented. So just as a space-saving convention of the formal specification, they will take the left leading list of constant instructions to represent the value stack, and reduction is defined directly on those, so kind of like a term rewriting system. So the way you read this rule is it's saying if you have 2 values on the stack and you execute a binary operation, then you will get back a single value on the stack, which is the result of applying that binary operation to the 2 values you popped off. And there's also another possible reduction for binary operations, which produces this trap error. And that's reserved, for example, if you divide by 0, you'll get an immediate error that halts execution of the program. And here's just one more example of a stack manipulating instruction. This is WebAssembly's ternary operator, select. And the way select works is it requires 3 things on the stack. First, an I32, which is interpreted like a Boolean. So if the I32 is non-zero, then it will select the first value on the stack. And if the I32 is 0, it will select the second value. And these V meta variables are just standing in for constant instructions, or equivalently values on the value stack for which we don't care about the type. So aside from purely manipulating stack values, WebAssembly deals with 4 core kind of parts of its state. It has local variables, global variables, heap memory, and the function table. And I'm going to be describing the first 3 of these explicitly, and the function table isn't really required for the rest of the talk, but it's to do with indirect calls, basically. So to start off with, local variables are very simple. They are declared per function, so each local variable is declared in scope of the entire function. And over here, I have a little program fragment of WebAssembly. This is actually declaring 2 local variables. So first off, all of the arguments to the function are turned into local variables when they're exposed to the function body. So I'm declaring 1 local variable here, which is going to hold the argument to the function. And I'm also declaring a second scratch local variable here, which will be 0 initialized. And when you refer to these inside the function body, you just use very basic De Bruyne indexing. So this local.getZero is getting the value of the function argument. I'm adding 1 to that, and then I'm putting the value back into my scratch local variable. And here's the formal semantics for that. So the reduction rule now involves the frame, and it's just exactly as you'd expect. The frame contains the function local information, including the values of all of the current locals. And if you're doing local.get, you just go into the frame and pluck out the appropriate statically indexed local. And similarly, if you do set, you go into the frame and you modify the value of the appropriate local. So global variables are declared per module. And in fact, they can be shared between modules if you import them. So first, I'm declaring a global variable, which I'm just importing from the environment. And this could have been declared by another WebAssembly program or module that I'm importing now. And I'm also declaring a second one of my own global variables. And then this function body is just very simply getting the value of the first global, which is the one I imported, adding 1 to it, and then setting the value of the first global to be equal to that value. And the formal rules for this require a bit of indirection. So now we're involving the global store, which, as I said, contains all of the globally allocated state. So this is where the values of the globals list. The store, the values of the globals live. The store will contain a canonical list of all the globals that have been allocated across all programs. And then the frame will tell the current reduction which globals are in scope or which globals are accessible during the execution of the current function. So in order to execute global.get, you have to go into the frame and you have to look up where the kth local is in the store, and then you go and modify the right global in the store. And then similarly for set, you have to go into the frame, find the right global variable so you can correctly update the store. And the final part of WebAssembly's state that I'm going to be introducing is the heap memory. So WebAssembly allows you to manipulate this very simple linear buffer of bytes. So here in my program, I'm declaring a single linear memory, and this 2 refers to the size of the memory in pages, and each page in WebAssembly is just 2 to the 16 bytes long. And then here within my function, I have an index into the memory that I will put on the stack, and then my load operation will go and access the memory at that index. So this is saying get the value at byte location 100 of the linear memory and return it. And the memory is 0 initialized, so you never have to worry about reading uninitialized values during execution. So here is the formal semantics for that, just as you'd expect. The store tells you where all the what the state of all the memories that have been allocated are, and the frame tells you what your current memory is that you're allowed to access. And then when you execute a load, you have to go into the frame, find the appropriate memory. Now, the interesting thing here is all accesses to the memory are actually explicitly bounds checked. So if you provide an index to the load, which is greater than the bounds of the memory, you'll immediately get this explicit trap error, just like when you divide by 0. Otherwise, execution is allowed to proceed, and you pluck out the appropriate bytes from the memory to reinterpret as a typed value on the stack, according to the type annotation of the load. Similarly, store interacts with the memory. So one point here is that in WebAssembly, the index into memory is always an I32. So this type annotated store is storing a 64-bit float at the address 120. So this constant value, this 3.5 64-bit float, will be turned into bytes and just linearized into the memory by the action of store. So here again is the formal rule for store. 2 arguments. The first, the index into memory. The second, the value to be stored. If the access is out of bounds, then you trap. Otherwise, you reinterpret the value as bytes and just linearize the bytes into the linear memory. So there are 2 other instructions which manipulate WebAssembly's linear memory. Because I described how linear memory can be declared to be a certain size at the start of execution, but you are allowed to dynamically check and change that size during execution. So memory size will just return onto the stack the number of pages currently allocated in the current memory, and memory grow will take a value off the stack and increase the size of the memory by that many pages, and the bytes of the memory are just automatically zeros during the growth. So again, no uninitialized values. So the final part of WebAssembly, I've talked about WebAssembly's kind of straight line code that interacts with its state, but the most interesting part of WebAssembly to me is actually its kind of slightly non-standard control flow, especially for a bytecode language. Unlike, say, the bytecode language of the JVM, WebAssembly has entirely structured control flow. Instead of having a goto instruction, you actually have these type annotated block and loop instructions and a structured break BR instruction, which interacts with them. So an example of this is here, I have a block. So this is actually WebAssembly's AST. In the actual bytecode of WebAssembly, you will literally have a block bytecode, and then later on you'll have an end bytecode. And all of the operations in between those 2 bytecodes will be in the AST interpreted as being in the body of the block. And the semantics of BR inside a block is if you execute it, you simply jump all the way to the end. So anything in between is going to be dead code. And this functions like a break in a higher level language. Now, the interesting thing is that there's also this loop kind of structured control flow expression. And loop doesn't work quite like you'd expect. If you have a loop and just some regular calculations inside, then the body of the loop will only run once, and then the loop will immediately terminate. The way you get a loop to iterate is by targeting it with a BR instruction. And whereas with a block, a BR instruction causes execution to jump to the end of the block, in a loop, a BR instruction causes it to jump to the start of the loop. So in fact, this code fragment depicted here is an infinite loop, because when you execute the BR, you'll just keep on transferring control back to the start of the loop, and you'll just iterate forever. So here's a slightly more complicated example that also shows conditional control flow. So BR doesn't just always target the innermost control flow construct. It can also index outwards to more distant ones. So here I have this BR if, which is a conditional break. It pops one value off the stack, and if the value is non-zero, it will act like a regular break. And if the value is 0, it will do nothing and execution continues. And because I have this 1 here, it's actually indexing this outer block. It's counting outwards. So this would be 0 and this is 1. So if this BRF successfully executes, execution will jump all the way to the end of the block. If this BR executes, execution will jump to the start of the inner loop. So the way to interpret this code is I'm getting the value of the 0th local, which may be the function argument, for example. I'm checking to see whether it's greater than 10. If it is greater than 10, I immediately jump to the end of the block and stop execution. If it's not greater than 10, I increment it by 1 and then go back to the start of the loop to check again. So effectively, this is iterating until the value of the local reaches 10. So the typing of control flow constructs needs to, the typing of control flow constructs needs to take into account that when you are transferring control to the start or end of a block or loop, you need to make sure that the shape of the stack matches up with where you're moving control flow to. So in addition to using the straight line type, which describes how the stack is transformed if you just execute the code in a straight line, you also have to have this auxiliary label parameter, which keeps track of what the shape of the stack should be at the point a break is executed. So here you can see a block will put its output type onto the kind of the label list. And then when you have to go in and type a BR, you look up which label you're breaking to, and then you have to make sure that the appropriate type is available on the stack at that time. So at a top level, WebAssembly's formal specification defines exactly the correctness condition that its type system is meant to guarantee. And it is absolutely bog standard syntactic type soundness from the literature, which I think is just completely wonderful. So this property is made up of two different parts. You've got progress, which says if you manage to successfully validate a program, it's either going to terminate with a result or it can always be run a bit more. And the implication of this for WebAssembly is if I'm executing, say, an add instruction, which will only execute if there are two things on the stack, the type system guarantees that the stack will always have enough values for that add to successfully execute. You won't get a stuck error because there weren't enough values on the stack. And the implication of this is you don't need to dynamically check the stack in a real implementation. You can always guarantee there are enough values there. And the second part of this preservation just says that if you manage to successfully type a program and then you execute it a bit, the intermediate reduct will have the same type, which is exactly what you would hope for. So just to really tie into my point there about progress and preservation and what this means for real implementations, because you statically know that the stack is always the right shape to allow execution, in a real implementation, you don't actually need to simulate a push and a pop. So a push and a pop in WebAssembly's semantics to the value stack actually don't imply any computation at all in real implementations. You can just statically link up all of the stack operations with the things operating on them. So this means the conversion from a WebAssembly program to SSA is completely trivial. So here's like a very simple example where you can just change effectively these const instructions, pushing onto the stack to them assigning to local variables, and then you just wire up all the local variables in the right way. But it even extends to much more complicated programs involving control flow and breaks, because the type system will always make sure that at the point you execute the break, so here if I execute this break, I would be transferring control to the end of this block. But WebAssembly's type system will make sure that this is just exactly like having a very simple phi node with exactly the same number of local variables in both cases. So the transformation is very simple. And you shouldn't think of WebAssembly stack as actually being something that is involved in real computation. It's just effectively an artifice for naming an infinite number of local variables implicitly. So I've given you kind of a rundown of the structure of WebAssembly's formalism as it appears in the spec. And because WebAssembly has done such a good job of exactly defining what its execution model is and exactly defining what its type system is and exactly defining what properties it expects of both of these together, this is absolutely wonderful for mechanization because all of the kind of grunt work of subjective interpretation of the meaning of the language is done for us completely. So I actually went away and did this. I plugged all of WebAssembly's definitions into Isabelle, translated them from a draft of the specification, and I investigated whether it was actually possible to prove the type soundness property that they claimed of their formalism. And in the original draft I was looking at, there were actually some mistakes. So I was able to go back to the standards committee and kind of talk through how the spec needed to be changed, sometimes in small ways, sometimes in slightly larger ways, in order to actually get this type soundness property being actually true. And once all of this had been done, I was able to push through the whole type soundness proof in about 11,000 lines of Isabelle whole. And then on top of the mechanization, I was able to build a verified type checking algorithm and a very basic runtime interpreter that's verified against the operational semantics. So having built this mechanization, you obviously want to build things on top of it. And one of the first things we did was build a nice little program logic, because one thing we kind of noticed was WebAssembly's type system has this very beautiful static structure. And you'd expect to be able to build a program logic which just looks very similar and enjoys the same kind of static structure of invariants you know about the state of the stack and things like that. And it actually worked out really well. So without going into too much detail, I've already shown you the typing rule for block, where you have to keep track of what the output type is in this label context. And the version of that in the proof rules is instead of keeping track of a type, you're keeping track of an output assertion, effectively. But the rules just look so wonderfully similar that I just think it's completely beautiful and neat. And all of the proofs are really nice as well, because it just shows how all of the invariants about WebAssembly's type system also ties into neat properties when you're reasoning about it. So I had worked in a pause for questions here. I'm looking at the Slack. I don't see any questions, but I don't know if there is another source of questions that could be checked.
No, that's what I reckon the source is, though if anyone wants to speak out on those things. Let's go.
Shall I continue then?
Yep, you do that.
All right, so I've talked a bit about the basic WebAssembly structure and the mechanization we built around it. And now I'm kind of going to put on my other hat and talk about some more hypothetical extensions to WebAssembly before rounding back to the work I did very closely with the standards committee on the relaxed memory model. So one thing that I've kind of looked at with a group at UCSD is the fact that, unfortunately, a lot of cryptography on the web has historically been written using JavaScript. And this just goes back to what I was saying before. For years, JavaScript was the only game in town. Nothing else has been able to match its ubiquity. So as bad as its security properties are, it often is just the right choice from a developer's point of view if you want to write a cryptographic function and have it run the same on a user's client in their web browser and on the server and just be able to share that code everywhere. So WebAssembly just existing as it does is already a great step forward, because now all of this cryptography can be written in WebAssembly rather than JavaScript. So that's just a wonderful leap forward just to start with. But we were wondering, well, can we do even better? Because WebAssembly has this nice type system. And there's this concept in the field of cryptography called a constant time discipline, which is where you write your code obeying these absolutely ridiculously kind of simple restrictions on information flow and a white list of instructions you're allowed to use. And there's a kind of an expectation that if you write your code in this way, it will have better properties and it will be harder for attackers to exploit. So the question is, can we turn these kind of disciplines that programmers are following into just very coarse-grained restrictions in the type system of WebAssembly, and then you can type check this property automatically? So we were actually able to do this. The modification was very simple. You add explicit secret types to the language, and then you turn mixing secret and public types in computations as explicit type errors, which represents effectively information flow violations. And then also you say that secret types can't be used for conditional execution, because that exposes a side channel, a timing attack. So you just say, if you want to do conditional execution, it has to be on a value you've marked public. And these are very, well, actually, there's one more restriction as well, which is when you serialize values into memory. Say I have a secret value that I want to store in memory. I don't want to then be able to deserialize that value as a public value, because that would break our information flow property. So we also add this capability to mark memories as secret, and then you're not allowed to store a public value into, excuse me, you're not allowed to load a public value from a secret memory. You have to explicitly type annotate your load as secret. And the interesting thing here is that the index to the load is still public, simply because it's revealed by cache timing behaviors. So that's something we have to do. So these restrictions are very coarse-grained. They're very brutal, but it turns out the vast majority of cryptography that exists, like modern cryptographic algorithms, actually do fit inside this type system, simply because it's considered the good way to write cryptographic code, because you can be pretty sure it's resistant to certain timing attacks. So we were able to very successfully implement a bunch of different cryptography using this kind of hypothetical type system extension. And I also went away and I mechanized the type system extension on top of WebAssembly's base mechanization, and successfully proved that this type system, if it's followed, will give you these constant time security properties. So the type annotations also do something else. So aside from allowing a user to effectively check the code to see if there are these constant time violations, they also give enough information for the compiler to know statically that it needs to be careful about what optimizations it does. So for example, you remember the select ternary operation. which select one or the other value from the value stack. This can be compiled in two different ways. It can either be compiled using a constant time conditional move on platforms that support it, or a bitwise operation on platforms that don't. Or you can compile it using a branch. And if you compile it using a branch, then that actually causes timing vulnerabilities. So if you have these explicit secrecy type annotations, then a compiler can know to compile select in a way which is constant time safe. So we went and brought CTWASM to a discussion in the WebAssembly community group, which is kind of the body where proposals for official incorporation into the language get dissected and discussed amongst different implementers. And we kind of did have this discussion about how really CTWASM is doing two different things. Firstly, it's protecting the user in a sense, because the user can see a type error if there's some information flow violation. But secondly, it's protecting the compiler and the intention of the original producer from, if the producer wants to write constant time code, then they have enough type annotations to make sure the compiler won't later go on and muck it up. And the kind of consensus broadly amongst the different engine implementers was they were much more interested in the second use case for CTWASM than the first. They didn't see it as the role of the type system to allow a user to check a security policy in this way. They much more saw the role of the type system as ensuring the compiler can compile in a safe and expected way. So the kind of version of CTWASM that would be more palatable to them probably wouldn't in itself guarantee constant time, but it would be a much lighter proposal so that a producer of CTWASM could write the code in a way that the compiler won't violate constant guarantees if they were originally built into the code. So we would probably, for example, omit explicit type annotations on memory and such like, and just trust the producer to produce code that respects those invariants, even if they're not actually explicitly checked by the type system. Yeah, so this is just a kind of a diagrammatic idea of this. They're much more interested in the producer knowing about making the correct types so that the web browser can produce the correct code, rather than having types that the web user can use to check that the producer was doing their job correctly. So I'm seeing a bunch of new questions now. I can do a second pause before talking about the next bit.
Okay, I think that would be good because we've had a few about very much the basics of
exactly.
WASM. So off the top, there are questions about, can you give an example of a mistake from the original WebAssembly? So when you put it into Isabel, what did you show up that was wrong?
So probably the most wide-ranging kind of error in the draft specification was the description of how WebAssembly interfaces with JavaScript. So I've described how WebAssembly's type system and just the operational semantics of WebAssembly maintains all of these invariants about how the WebAssembly state is allowed to evolve over time. But when you embed WebAssembly inside another language, and then you expose all of WebAssembly's state to that other language could have a lot more power to go in and mess with WebAssembly's internals in a way that it doesn't expect. And so within the specification, there's this contract defined that the host won't do too many egregious things to the WebAssembly state. And so that emerges effectively as a big list of axioms the host has to follow in guaranteeing how it's allowed to modify WebAssembly's state. And originally, there were some axioms missing. So notionally, the spec was saying, oh, the host is free to go and do this and mess with a bit of WebAssembly state. The big one would be, for example, something like it could go and dynamically change the type of a global variable or something like that from a float to an int. And then the WebAssembly code itself doesn't expect that. So you could dynamically get something going wrong. So just making sure that the spec actually accurately listed all the things the host had to obey when interacting with WebAssembly was, I think, the most kind of general thing that was going wrong with the spec. And there were also just some smaller things like the wrong type annotation or a typing rule missing some side condition or something like that. But that was the kind of the biggest thing. Okay.
So the question, can you deal with function pointers?
Well, the way WebAssembly deals with function pointers is using the table, which I I'm not really describing. The table is effectively a big list of function closures which you can dynamically index into. And you can't directly have function pointers represented in the heap, but you can have an indirection where the heap stores an index into the table. So it's a little more expensive to do kind of function pointers in this way, but it's expressive enough that you can compile them.
Okay, one more question, I think move on, which is why is BR so unintuitive for the different kinds of loop?
Well, I'm not going to defend every design decision. It's not, it's surprising for a second. And then I think once you've got used to it, all of the kind of other bits of the model flow from that. I did talk to one of the designers who said if they could travel back in time, they might have made it so BR only works with blocks and loop really does just loop. And then you use a BR to break out of the loop into a block. So that could have been an alternative design, but it's just not what happened. And you're right that it's a tiny bit unintuitive, but in the grand scheme of things, everything still works.
Okay, great, thanks.
Yeah,
we can come back to others later.
I think I'll just continue and then I'll have another pause for questions at the end. Okay, so another kind of security property of WebAssembly I've been looking at with this UCSD group is the property of memory safety of the actual linear memory. So I've already described to you how accesses to the memory in WebAssembly are bounds checked. So you can't access an index which goes beyond the bounds of the declared buffer. But if you're compiling a source language into WebAssembly, if you have two heap objects, the way those heap objects will be represented in the compiled WebAssembly is just as bytes laid out in the linear memory next to each other. So an access to one object, if the arithmetic goes a bit wrong, can overflow into another object if the correct access checks aren't done. So here's kind of a concrete example of this. I could have a C program where I have an array of like safe data that I expect an untrusted person to be able to access. And I could have an array of secret data, which might be my private key or something like that. But maybe I'm exposing this API function where I'm allowing someone to get a character from my safe data. But unfortunately, I forgot to check the offset I allow them to provide. Now, in the compiled WebAssembly program, the safe data and the private key, the password, will just be laid out next to each other in linear memory. And this pointer access here will just be compiled to a regular load with arithmetic done on the index to make sure it gets to the correct value. So if I pass in a massive unchecked offset, X will start here, and then the arithmetic could just go all the way over into here and get some characters out of the secret data. So this is basically exactly like Heartbleed. I should stress, though, that you still can't overflow beyond the bounds of the linear memory. So this is only an issue if you have a compiled program into WebAssembly where you have kind of mixed objects where you care about some of them and you don't care about other of them being accessed. But this is a situation where you could potentially see a real security vulnerability here if your original C code doesn't do enough checking of pointer offsets. So, question, could cherry style capabilities in WebAssembly help with this? I believe there are other talks going on about cherry's object capabilities in this new kind of paradigm for architecture. And could we expose those kind of checks at the WebAssembly level? And then could that give people who care a more secure way of allocating these kind of heap-like objects? And we've done some preliminary work on what would an extension look like, what guarantees would it give you? And I think potentially it might be a little difficult to standardize this in WebAssembly right now, because there aren't that many real architectures that actually provide capabilities. You would have to kind of mock it in some way on every other architecture. So I think we would be able to make a much stronger case for this to be adopted in a world where there are multiple different architectures with capability stuff. And maybe Cherry is the first step towards that. So finally, and I see I don't actually have that much time left, I'm going to talk about the relaxed memory behavior that I've had to work with for WebAssembly. So I've already described how WebAssembly can load and store to linear buffers of bytes. With concurrency, you can now have multiple threads accessing one buffer at the same time. And this instantly gives you relaxed memory behaviors, where you can no longer explain how the program is executing as a sequential interleaving of the individual accesses. So you need to define a relaxed memory model to describe all the things that are allowed to happen, and perhaps more importantly, the things that aren't allowed to happen. So the interesting thing here is JavaScript and WebAssembly have to interoperate pretty closely together. JavaScript already has a specification for threads and its own specification for a memory model. And the JavaScript and WebAssembly committees, which have considerable overlap, kind of had this idea that the memory models should be basically the same for the fragment where JavaScript and WebAssembly have like overlapping behaviors. So a JavaScript access and a WebAssembly access should look pretty interchangeable. So the path of least resistance is to make a lot of WebAssembly consistency behavior inherited from the JavaScript memory model. So the first thing to do is you have to go and fix the JavaScript memory model. And we went away and did this. And in fact, this will be talked about in PLDI in a few days. So I won't go into too much detail, but there were some issues we found, some things we corrected, and some verification we did. Having done this, we then need to extend the WebAssembly model on top of this JavaScript base to describe all of the extra features of WebAssembly that JavaScript doesn't have. And the key one here is memory growth. So in JavaScript, the size of the buffer is fixed. In WebAssembly, it can grow. And this can create a new kind of race condition based on bounds checking. So here intuitively, in one thread, I'm doing a load of y, which is this location here, and y is out of bounds normally, but if I execute this grow, then it will become in bounds. So intuitively, the way this program works is, you would think, if I successfully load y and don't get an out of bounds error, then this load of x must see 42. It won't see something older, because the grow must have already executed. But is this true or not? Well, we have to look at real implementation to determine whether our model can forbid this a more relaxed behavior or not. In a naive implementation, the way bounds checking is implemented is you actually have an explicit bounds check and a branch, so that you, with every WebAssembly access, you have to explicitly check the length of memory before you actually do the access. And then a growth of memory is just turned into atomic modification of this length location. So you have pre-allocated a bunch of memory, and you just have this length location, which has to be explicitly checked in order to implement WebAssembly's bounds checking semantics. And it turns out if you compile this to ARM, you really will actually see the relaxed behavior. So even if this read succeeds and says that the load of y is in bounds, it's possible for x to see a value which is older than 42. So that's an immediate clue that our relaxed memory model has to be a bit weak for how bounds checking information propagates between threads. And finally, I'm going to talk about a more optimized implementation of bounds checks that we actually have a lot of trouble verifying right now. Which takes advantage of the fact that virtual memory is really cheap to secure and reserve, as long as you don't actually put it into RAM. So you just reserve a full 2 to the 32 byte address space. That's all the addressable memory a WebAssembly module can access. And you read and write protect all the virtual pages beyond the bound of the current WebAssembly memory. And then if you access in bounds, everything works correctly. If you do an access which is out of bounds of the WebAssembly memory, this turns into a page protection fault, which you can then catch and turn into a regular WebAssembly trap. So you can see in this implementation, you no longer have to do an explicit bounds checks. You can just do bare load and you can just do bare assembly loads and stores. And memory growth is just turned into an unprotection of these 2 pages of virtual memory that we reserved. And then off to the side, there's this trap handler, which will catch if we do an out of bounds access and turn it back into a regular WebAssembly trap. And we're not actually able to completely verify whether this implementation conforms to our model right now, because we need much more sophisticated formal models of TLB semantics and exceptions and caches and all of this sort of thing. But implementers have made a kind of commitment that we can base our semantics on the more explicit bounds checking implementation, and they will make sure that this more optimized implementation doesn't have any surprising weak behaviors. So that is everything I have to talk about. Thank you for listening, and I will continue answering questions.
That's grand. Thanks, Conrad. So we are now into general discussion between the sessions. Thanks very much. The next talk will start at 5, but Conrad, if you want to pick up what's in the Slack channel. Oh, actually, there's up there, there's one upvoted question. Not there's an official mechanism for that, but there've been little pluses people have been putting in. And that's that having an official formal specification of WebAssembly and a program logic looks like a great opportunity to write a formally verified compiler targeting WebAssembly. Are you aware of any projects doing that?
So I am aware that there have been various mutterings in the CakeML community about this kind of thing. I'm not sure how far it's got, but I know people have been kind of thinking about it and looking at it. Yes, I think it would be great. I think WebAssembly is a great language to try and do this kind of thing with, both compiling to WebAssembly and compiling from WebAssembly. For example, and I unfortunately forgot to mention this during the talk, so forgive me, Philippa. We're currently working on a COC model of WebAssembly, and that would be wonderful, for example, to hook into CompCert in both directions, because then all of the other proofs are done, and you can kind of just link in the WebAssembly level of semantics and get a lot of kind of beautiful compilation correctness proofs for free.
Okay, after that, I suggest you might want to have a look at the stream yourself to see which things you can pick up.
Absolutely. Thanks very much.
Right, thanks, Conrad, and we'll meet again at 5 o'clock. Okay, Yannick, that looks fine. I can see the screen.
I said thank you a few seconds ago, but I was muted.
Okay, now I can see and hear you, which is good.
Perfect.
And I guess everyone else can too. There's a specific thread in Slack on the Slack channel for questions for this talk. You can either look at that yourself or I can relay them at the end.
I will have it open on my second monitor, but I cannot guarantee that I will manage to catch up everything on the fly. So feel free to interrupt me, of course, at any time.
Right, that's fine. By default, I think we'll leave it till the end, unless you have a specific point in the talk to break. Just leave it to the end.
Yeah, it will depend, I guess, on the timing. I might make a breaking point in the middle. Yes.
Okay, that's fine.
Thank you.
I guess you don't also have the conflict of co-authors answering questions on the channel at the same time as you're giving the talk, which we've had elsewhere. I mean,
Sure.
It's good, but it gets confusing.
Yes. I can imagine so for sure. I'm sure we will manage. No worries. Right.
So welcome back to those coming for the last session of the REMS-DeepSpec workshop. I've just heard that there may be a competing chair for this session. I wonder if one of the hosts, Leonard or Peter, can you clarify?
Just a second, yeah. Yeah, Steve is not yet back, so why don't we just start? And I'll just start recording now.
Thanks, Leonard. So welcome back to the final session of REMS-DeepSpec workshop. Our first talk in this session is Yannick Sokovsky, who's going to talk about representative recursive and impure programs in COC. there's a discussion channel thread over on the Slack channel, which I'll post a link to in the chat if people have questions during the talk, and then we can relay them to Yannick at the end. Thanks very much. Yannick, away you go.
Thank you very much for the introduction, Jan. So indeed, we're going to talk about representing recursive NPO programs in Coq, and more specifically, we're going to talk about the libraries that is called the interaction trees. So if you happen to have seen maybe the talk by Liao back in January, then you can think of this talk as a more in-depth technical journey through the detail of the library and its use in particular, otherwise consider it as an introduction. So I will just start with a little bit of historical motivation. So we are in this context of this DeepSpec project that you have heard of quite a bit for now. Also, in particular, it is this peculiarity to host numerous wonderful projects of formal verification. And one of the ambition of this journey was to actually be able to combine these different projects that, despite having been developed fairly in isolation, should be able to be combined to obtain some kind of full stack verified software. And it turns out that this is far from trivial to actually interface together formalisms that are fairly different despite all being hosted in the same proof assistant. So one of the emblematic examples of such a project was the DeepSpec server, is still, excuse me, the DeepSpec server. So one way to put things is that what we intended to do with interaction trees is kind of to be bombastic, to have a franqua lingua of specification, to be maybe more modest, at least some kind of mortar that could be used to interface with different projects. Having such an ambition is kind of like immediately shape a list of constraints that we have with respect to the model that we're trying to develop. We want to be able to model very diverse specifications. So we are looking for something that will be parametric in the type of interactions that the specification we are considering can have with its environment. We are also looking for something that really has to be tied to, and formally tied to an executable, to actual runnable code, in part because we want to be able to conduct testing in parallel with the formal development, in part because we want to derive definitional interpreters that are formally tied with the semantics we make proof about. The third aspect, of course, is the obvious constraint that we are living in the Coq proof assistant. So this is something that is well known to probably all of us here, but we of course have to live with this tension between the strongly normalizing pure aspect of Coq, of this meta language, which is in complete opposition with the generality of the language you're trying to formalize. So this is of course not a problem at all if you are using small step propositional, for instance, approaches to formalizing your semantics. But if you want to maintain this ability to be executable, then it becomes a lot harder to work with these constraints. And the last aspect, of course, is that we want to be able to use this semantics to conduct large-scale proofs. So we will have a desire for modular specification, and in particular notions of equational reasoning. So this is just for the high-level motivation. And now through this talk, we basically kind of go through the various features of interaction trees, starting from their definitions and the core idea behind them, and then using a toy language in IMP in order to introduce progressively the way you actually use them to denote a language. We will therefore first see the first notion of denotation of IMP program, then the notion of handling events, which is the part where you give a semantics to the effects of your program. Finally, we will consider application of this framework to verify a compiler, and conclude with some proof of concepts that this approach are not reduced to simply IMP or such toy languages, but actually scale, where I will talk to you a bit about the ongoing work that we have to formalize LLVM's intermediate representation using these approaches. All right, let's start with interaction trees per se. So the kind of high-level selling point is that with interaction trees, we are giving you a Coq library. And I should mention on the left that here are all the fine authors with which we wrote this paper. So we are providing a Coq library that gives you all the tools that you need to define a semantics in the Coq proof assistant, but that has the peculiarity to satisfy three properties that are not that trivial to recover with traditional approaches. The first one, of course, is this idea of compositionality. So that is always very tied to this idea of denotational semantics. You want to be able to define your semantics by recursion and the syntax, and hence to reason about it by induction and syntax. Second aspect is modularity, which has to do with this idea of algebraic effects. You want to be able to define each of your effects of your language in isolation and to compose them without having to introduce additional syntax. And finally, the executability that we've been discussing in order to be able to conduct tests. And so we provide tools to define semantics satisfying these properties, but also equations to reason about these semantics. And of course, the project is available online if you want to toy with it. But let's dig a bit more concretely into what are these interaction trees. First and foremost, at its core, it's a data structure. So it's a co-inductive data structure where each value of the data type represents a computation. So it's really a shallow embedded domain of computation embedded in Coq. So the fact that it's co-inductive, so this idea of a lazy data structure, allows us to represent potentially diverging computations. Now, of course, the computation does not have to be infinite. It might return, and it returns a value of its second parameter, of the type of its second parameter. This is a terminating computation through this first constructor. The core idea is that you are also parameterized by a domain of events, so some sort of interface E, which is a family of type. And this family of type embedded all the way your computation can interact with an environment. And so through this third constructor, this idea is that you emit an event E, whose semantics is not presupposed, and you carry on a continuation indexed by the return type of the event that will explain how the computation is meant to continue once the environment has returned the value corresponding to the event. And finally, both for technical reasons related to the notion of co-induction, but also in order to be able to represent the silently diverging computation, you may have internal silent steps. So this is the data type. If we just step back a moment, if you happen to know the domain and to know the related work, note that it's of course a co-inductive implementation of the FLIR monad. If we want to be a little bit more concrete, here is an example of an interaction tree. So one value of a specific instance of this data type, where we consider for this computation that the interactions are read and writes to some notion of states. And so in this tree, we can see that we have potentially silent steps, some observable events, reads and writes. And in particular, this read is triggering an event that expects the environment to answer with some value, that is the content of the location X. And the computation, the tree, contains a continuation that, depending on this answer, will have different behaviors. For instance, can terminate with a result, or potentially might diverge, either silently or through several other effects. Now, the first notion of structure that we have about this interaction trees is the notion of monad. So this structure that allows you in particular to compose things sequentially in a neat way. So the definition is not particularly complicated. The return is simply the first constructor. On the bind, I omit here the definition, but basically, except for the fact that we have to write a cofix point, it is a straightforward crawling through the first tree until you find a value that you pass to the continuation. I will, of course, use in this talk the usual monadic notation with the semicolon, double semicolon. Now, when you talk about a monad, of course, you always expect to have some laws, the monadic laws that holds about it. So if you're not familiar with it, it's simply laws that explain that the ret can be simplified on either side of the bind, and the bind is associative. But never mind this detail. What is important when you state these laws immediately that stands out is that they have to hold with respect to some notion of equivalence of such computation, of such value trees. And this notion of equivalence, notably because we are considering co-inductive type, cannot be naively the equality, the Leibniz equality of Coq. So I won't be able to go into any details about the definition of this relation here, but know that if you are familiar with this kind of question, this is of course a quite traditional notion of weak-based simulation that we sometimes refer to as equivalence up to terms. But the gist of this relation is to say that two trees are related if they return the same value. You can match silent step on either side. You can also, of course, match identical event as long as the continuation agrees pointwise. But also you can remove asymmetrically finite amount of tau steps. And we perform this in a careful enough way that spin, which is a computation that is completely silent by divergence, so an infinite amount of taus, one after the other, is not related to anything. So the details of taking care of the definition on the meta theory of this relation is quite subtle, and it is described in our CPP paper if you want to know more. But in the context of this talk, what matters is to understand that this is the notion of equivalence that captures exactly what you want, the ability to ignore internal steps as long as they do not diverge, and otherwise matching of constructor one-to-one. All right, so this is basically the first basis, the definition of our data structure. So we have a co-inductive data structure named I-trees that represent computation, and that is parameterized in particular by the interface of your computation, that admits a model structure, and whose notion of equivalence is weak by simulation. In order to introduce more interesting constructions on this data structure, we will now consider a specific language, and we'll try to give it a semantics together. All right, so before jumping into IMP itself, I kind of like to give you a little bit of a spoiler so that you have an idea of the overall structure of the methodology that might clarify things. So if you consider here a trivial program, X receive 1, Y receive X, the only thing that I would like you to have in mind is that the way we give semantics to programs in this approach is made of two phases. The first phase will represent the program as one of these interaction trees, so with non-interpreted events. And then there will be a second phase that will take care of giving meaning to this event, so through a notion of handlers that I will introduce later, and that this meaning is given in terms of some monad. So you don't have to understand the details of this right now, but just to clarify things, what I will describe in this section is only the first phase. So let's jump into it. This time we consider this concrete language, IMP. So simple imperative language. You have assignment, sequence, conditional, and a while loop to make things interesting. And we want to give a denotation to IMP that is executable, and let's have in mind that it should be suitable to verify a compiler, kind of like a broad goal. And let's have this two-step process and start with this first phase, as I mentioned. All right, so once again, the one thing that we are trying to achieve, well, one of the things we're trying to achieve is to be able to actually define our semantics directly by recursion and syntax. So in particular, once again, so that we will be able to reason by induction on the syntax. So before even considering any of the constructors of IMPs, we need to decide what is this interface that determines the type of interaction trees into which we interpret our language. Well, in the case of such a simple language, really, we only want to consider two effects, read and write to the memory. We can take the opportunity to look into a bit more detail about this idea of this interface being family of type. When you perform a read to some variable, you expect the environment to answer you with your value. So you reflect this fact, in the type of this event. However, when you write a value to a variable, you only expect a side effect, don't expect any meaningful answer, so you reflect this fact in the type being unit. So now that we have fixed our interface, well, we can consider the first trivial constructor. What does it mean to give meaning to skip in this formalism? Simply to return unit. What does it mean to give now meaning to the assignment is a bit more exciting. I assume here, of course, that I have beforehand defined the denotation of the expressions of my languages. And the idea is that since I have a nice modelic structure, I can simply first denote my expression. Denotation that by itself could be diverging, but the co-inductive nature on the bind itself of the structure takes care of handling this case. I will, however, recover if it were to terminate some value v, that I can then pass to the following of the denotation that will essentially perform the write of this value v to x. To perform the write is through this small combinator trigger, which is essentially the minimal effectful computation that does this event. So the definition is simply perform this visible event E, and then continue with the continuation that just return whatever is answered. Next step, the sequence. Well, the whole benefit of having a monad is that the sequence is simply the bind of the recursive calls. The conditional is similar, except that we use kind of the meta-theoretic conditional of Coq. So we will first denote the guard, and then depending on the answer, denote either of the branches. And finally, of course, it becomes quite tricky and interesting when I talk about the while. So with respect to the while, well, of course, if you have ever seen any notion of formal semantics, you are very familiar with this idea that if I want to denote my while loop, I have a difficulty to define this by recursion. That's the whole pragmatic of the notational semantics. In the sense that intuitively, I would like to do exactly what I did for the conditional, denote my guard, and depending on the value, either simply return unit, I have nothing to do, or denote the body, and then denote the whole while loop again. But this would not be recursive, obviously. And so what we provide in the library is naturally a fixed point combinator that will allow you as a user to define by recursion this intuition. So how does the fixed point works internally? The idea is that if you look just this body argument, is that you consider that you have the body of a loop that takes as an argument the current value of the accumulator, and given this initial value of the accumulator, of this current value of the accumulator, will compute something, meaning will be an interaction trace that might either return a new value of the accumulator on the in left, so a bit of information that tells me that it wants to go back in the loop, or it will return a value of type B and a bit of information that will tell me that it's done. And the whole point of a fixed point combinator is that given such a body, it gives you the closure, it ties a knot and gives you a computation that given the initial values this time of the accumulator, returns a computation that returns a B. And it completely internalizes the potential intermediate returns of different values of the accumulator. And so the definition is naturally as a cofixed point. The idea is simply to evaluate the body, and depending on the nature of the answer, of the value returned by this body, either terminate by returning B if it has an in-right value, or get back to a recursive call to iter. And of course, that's where we use the tau constructor to guard these recursive calls. So if you're not familiar with co-inductions and details in code, this can be a little bit annoyingly technical, but the whole point of the library is that precisely what we provide you is a way to not care about these co-inductive details and cofixed points. In particular, that means that just knowing the type of iter, you can now define the denotation of this while loop essentially as you want it. That is, you call this iterator simply by considering an accumulator that is trivial, it's just unit, and we will just use the bit of information to go back or not in the loop. And so we are able to indeed denote our guard and either return unit plus the bit of information that tells the iterator that we are done, or denote the body and the bit of information that tells the iterator to go back in it. And once again, what is important is that as a client, you do not need to know anything about cofixed point to use the combinator. All right, so putting all of this together, we're able to give a first step of the notation of our imp language, once again, as a simple fixed point on the syntax. Now, this is kind of all fine and all, but so far, this semantics is kind of like some kind of glorified AST because we didn't give any semantics to our event. So we just changed the control flow. We internalized the control flow inside of this structure and through these combinators, but we didn't really give them any meaning. So that is the purpose of the second step. The second step is to handle events. So what do I mean by handle events is to get back to our signature for imp, so these read and writes, and to define a handler, which is to pick a monad of our choice. So here we will, of course, by default choose a state monad, and to explain how each of its events can be associated to an element of this monad. So more specifically, this tilde arrow, this kind of funny arrows, is simply a function lifted over a family of types. So let's make it concrete. In the case of this imp, let's assume that I am considering a state that is a trivial total map, just to not worry about technical details. the definition of the handler would be the one you would expect. In order to read a value in a certain state S, you simply return the same state S on the lookup of the value. And in order to write, you return unit, but with the updated map. So this gives a meaning to your events. But of course, the point is to give meanings to i3s as a whole. So as a user, what you do is only define the meaning on event, but then we provide a systematic way to lift this interpretation over trees. So that's the purpose of this inter function. Given a mapping from the interface E to a monad M, you get a mapping from an i3 of E into the same monad M. There is just some technical caveats. The caveats, excuse my poor English. We cannot do so in any monad. We can only do so in a monad that supports a notion of iteration. So the same way we have been able to define an iterator combinator over interaction trees, we need to be able to define the same kind of notion over the monad that we interpret into. However, this is once again technicality that as a user you don't really have to worry about, because as the iterator combinator illustrated it, the i3e monads support this instance, this class, and then all of the typical monad transformers that you might be interested in lift or rather preserve the existence of an iterator on the underlying monad to the lifted monad. And in particular, if you were looking carefully maybe on the slide before, that's why I was actually not handling my events into the state monad per se, but into the state monad transformer applied to the i3 monad. All right, so this is all fine. And so if we step back a little bit, we have now been able to denote the syntax of your program into some non-interpreted interaction tree data structure. And then we have been able to give a meaning to the event and leave this meaning to the whole interaction trees. And so the point is that once we are there, we can reap the benefits of the fact that interaction trees are simply a shallow co-inductive data structure in Coq. They do not rely on prop in the slightest, and so they can directly be extracted to an OCaml lazy data structure. So we just need to have a very minimal driver written in OCaml that basically just crawls the tree and whenever it finds a top, just keep going, looks for a result eventually. And if it happens to find a visible event, then it needs to handle it on the OCaml side. However, in the case of IMP, we only had one type of event in our interface, this read and write memory, and we have handled them. So all events are interpreted on the Coq side. So we know that we won't follow in this case on the OCaml side. But in general, we could also have the leisure to write unverified handlers in OCaml, and in particular in Velum, that's quite crucial to be able to print debug messages. So if we just kind of reach a first stopping point here, we kind of get like the general recipe of the approach. If you want to denote using interaction trees your language, you write down the syntax, obviously. You make an inventory of all the effects of your language, and you write the corresponding event interface. You use the i3 combinators to denote your language, so your syntax, into a non-interpreted tree over this interface. And then you handle the interface and get the interpreter for Wolfram for free, and the definition interpreter as a side product. I should mention that as much as you can apply this recipe for an enormous variety of contexts, however, being able to use the combinator in order to actually be directly defined by recursion in your syntax, this I can guarantee it for first-order languages on sequential ones, and other cases are very much up to debate and up to actual research. Should I take the opportunity to have a quick look? Michael Greenberg, you mentioned whether the two-phase denotation affects the efficiency of the extracted code and whether I can characterize the overhead of this abstraction. So there is definitely some overhead, which is essentially due to the implementation of the data structure itself in the way it very naively nests all these continuations. However, I don't have extensive data points, but one data point is that we are using this mechanism to execute LLVM programs in Velum. On it, we obviously did not try to scale yet to anything of significant size, but at least for our small examples, it goes at a perfectly reasonable speed. A second important point is that Oleg, I forgot his last name, I apologize, the original author of the FreeMonad paper described a trick to improve the speed of execution that we have not tried. So he described everything in the context of Haskell. So we have not tried to implement it in Coq, but if we were to have issues with efficiency, that's probably would be the first place we should dig into. But it really has, I think, more to do with the data structure itself than the fact that we are two-phased. Yes, thank you for the name. Oleg Kiselyev, my apologies. Adam mentioned that the cofix point was failing the project check. Unless I made a typo, I hope not. We can go back to this later if you don't mind. Maybe I made a typo, but I would be surprised. Peter Sewell. Yes, but the definition of our bind is kind of, we took some care of defining bind. I know that the first naive definition of bind was failing, but I'm pretty confident that this definition of iter with our current definition of bind is productive. I will come back to your question, Peter, maybe at the end of the talk. That's a little bit more in-depth as a discussion, if you don't mind. Thank you very much. All right. So at this point, we have kind of like, okay, here is this general recipe that allows us to give meaning to a language. Let me now try to turn to the question of actually using it to reason, and in particular to prove verified compilers. So the point of reasoning with interaction trees is to try to shield away every co-inductive proof from the user, and instead to reason completely equationally. So to do so, we kind of like provide a battery for each construction that we provide of equations that characterize its behavior. So naturally, the most obvious one are the monadic laws, but also we have a whole family of structural laws, as well as some congruence laws. So typically, when you want to relate two computations that are both defined as binds, then you should be able to relate each component in isolations. At least it should be sufficient. Monoidal laws, so we have essentially generalized notions of pattern matching on these computations, and so reasoning principles that are associated. Maybe the most important ones when it comes to avoiding co-inductive proofs, we have a set of laws characterizing the behavior of the loops of the iterators. In particular here, for example, we are able to unfold one step of the loop. And finally, we have equations that characterize the good behavior of the interp functions with respect to the underlying monadic structure and to the trigger combinator. So I don't want you, of course, to parse all these laws, but the gist of it is that we support setoid-based rewriting with respect to this with respect to this weak by simulation, so that as a user, you never have to unfold the definition of the combinator. You can just reason equationally. And in particular, you don't have to conduct prediction yourself. So in order to illustrate the use of this framework in the context of verified compilation, what we did is to write a compiler between this imp language that I have described and some kind of small toy assembly language. And for each of the language, you can go through this two-stepped process, given the notation in terms of non-interpreted interaction trees. Note that they are with respect to different interfaces, and then go through an interpretation phase where you interpret on each side the events into their own notion of state. So in particular, I want to emphasize that this sigma imp represents a notion of state on the imp side, while sigma ASM is actually a pair of registers on memory. And the idea is that then you can have a generalization. Sorry, we provide a generalization of our weak by simulation that is parameterized by some relations that allows you to relate heterogeneous computations, and by parameterizing it by essentially what behaves the same way as the simulation relation that you would use in a traditional proof of a compiler, in order to explicit how this notion of states relate on each side. one of the great side product of this approach is that we kind of like outsource the moment where we have to think about relating the control flow of each languages out of the moment where we actually have to reason about the semantics of the effect itself. And so we obtain the semantic preservation by wrapping this whole diagram. Just a few properties of the resulting proof that are quite satisfying. So this correctness is essentially the traditional correctness of, as you could find it in CompSert, for instance, but this time expressed as a weak-based simulation between your trees. The reasoning about the control flows is completely factored out. And to come back to this idea that we shift the user away from co-induction, the result is termination sensitive, and yet the proof itself is completely inductive, coupled with equation reasoning. So this experiment has been documented as a tutorial if you would like to dig into it a bit more. Julia Beliakova asked whether it is possible to express non-local controls such as exceptions. So it is absolutely possible to express it. In particular, in Vellum, we express function calls on returns that can happen at any point in a sense, and that cannot behave the same as exceptions. The idea in general is simply that you want an event that you want to give as an argument to the event the information that you need. The caveat that you have is that if you want to start to if you want your event to carry some semantics that has to be computed dynamically, so as soon as you get into higher order territory, essentially, it is possible to do so by passing some original syntax of your program in the event and then denoting it on the fly again, kind of in the style of the way Conor McBride did it in this paper about diverging program Turing completeness in type theory. However, you cannot lose the denotational aspect of your denotation when you do so. So the short answer is yes, you can encode anything, but you have to be careful if you want to remain recursive on your syntax. Also, there are much questions left open with respect to this domain for sure, to this question. Let me try to jump back, kind of like this is a good kind of first step. So we've wrapped up the fact that the idea that I try to convey that with this interaction trees, essentially you are able to have all the tools you need for a vast class of programs to denote them in a compositional way and have it in a way that gives you the ability to reason equationally about them. Now, the last thing that I want to tell you about is to try to convince you that it's not restricted to type languages, but it actually scales up. So to do so, we go back to this Vellum project that Steve initiated now 7 years ago with his co-authors in order to give a formal semantics of the LLVM's intermediate representation in Coq. And it was a major success, but it was using traditional approach, so a small step propositional semantics, and ended up being in a state where it was very hard for it to evolve anymore. Well, it's in his own world. I don't feel comfortable criticizing his project, of course. But so what we have been trying to conduct, and that we have been conducting for the last few months, is to now redefine the whole semantics in a compositional, modular, and executable way using this approach based on interaction trees. And so this time it's a joint work with Steve, Kevin, and recently Irene has joined us. And we also have a collaboration with Vadim Zaliva to prove a front end. This is, of course, also available online if you want to browse it. I will not be able to go into much details about this semantics, but I want to try to give you like high levels intuitions about how both the complexity scales up, but things still works out. The first idea is that quite satisfyingly, we had a general recipe. Turns out that we can just follow it. So since we have luckily inherited this abstract syntax from the first version of the project, we can start by just inventorying the effects of the language. So this is a piece of syntax, of LLVM syntax and control flow graph. And so we have some kind of operations that basically do local computations. So we first need to acknowledge for some local states that will be similar to what we saw before, some read and some writes. I will skim over many details that I will be happy to go flying through, but please don't try to read in too much details what happened on the screen. But the idea is that, once again, local states, essentially the same notion of states as we had for INF. However, this time, well, we also have a global state. So let's just make it a separate domain of events. We, of course, also have memory events. So this time, it's going to be something a bit more heavy. You have events to represent allocations, push and pops of stack frames, loads, stores, get element pointers, which is the way LLVM access structure, data structure. Oh, I'm sorry, I have a typo, but conversion from integer to pointers and from pointers to integers. If we keep going, well, of course, LLVM program is a set of functions, of mutually recursive functions. So here we have a return, so we also have calls. Because we have functions, we have also stack frames of local states. And then we have a few more technical ones. We need something specific to handle phi nodes, which are a peculiarity related to SSA nature of the language. We have some way to handle the non-determinism of the language that has to do with undefined values. We have some way to model undefined behaviors, some debugging message to help us develop, and some failure to detect bugs in our compiler. So the general message is we can do the inventory, but certainly things got a bit bigger than they used to be. However, we can just next go to the next session. Let's use the combinators to denote our syntax over this signature. Well, if we go back to there, the gist of it is that obviously, if you open the box, things are quite big. There is a lot of details to work out, but the combinators are expressive enough so that we can get started by denoting the expressions. So we have an I tree that returns some kind of value. Then we can build on top of it the denotation of the instruction, that this is just a side effect instruction, so it will return the just unit. We can denote terminator, so the jumps are the return. So this returns a block ID or a value, on top of which we can build the denotation of blocks, and then of control flow graph, which is what in LLVM represent functions. So this one is a bit more tricky, but without getting into details, if you're interested in the idea is that you can express it as a fixed point over this denotation of blocks, where you consider your accumulator as the block ID, that is the address toward which you enter your computation. And finally, whole programs are denoting using a mutually recursive combinator for fixed point. All right, this is the last high-level point that I want to describe, handling all of these events. So in the first case, where we were just taking our set of events, handling them in the state monad, the bird's eye view idea that we have is that we go through successive phases of interpretation, where each interpreter will interpret away one of these elements in the signature. So once again, no need to get into the details, but here note that the starting point is this denotation of the whole abstract syntax into uninterpreted trees. And you can, for instance, notice that here, there is a step where we interpret away the memory event. And you have to understand that behind this handler, this time is not a trivial state monad, but the implementation of the whole memory model of LLVM. Sequential memory model, excuse me, I should have made clear since the beginning, we only talk about the sequential fragment of LLVM here. Finally, since we have now some non-determinism in the language, we have this interesting idea that we can share all these first passes, but branch at some point between a decidable executable interpretation, so that define one specific handler, and a model that collect in prop the set of execution, and we can prove formally that the definition interpreter is one of the behavior captured by the model. Now, if you want to prove a compiler, you want to know what is the notion of observational behavior of your programs. So it's basically wondering, after having went through this whole model, what remains in your signature. And so the point is that remains external calls, debugging messages, and failure. So the model assumes, of course, no debug and no failure, but you observe uninterpreted calls and return values. So essentially what Comster does. On the executable side, however, we can have an example of a no-camel side handler and print our debug messages. that leads me to my conclusion. I have left lots of interesting detail with respect to this Velum project. It's quite a particularly suitable application, is that it raises problem but is still tractable. And so here are a few examples that I would love to discuss offline if you're interested in. But if you want to go into further detail, please take a look at the project. I would be happy to answer any remaining questions. All right. I went a bit overboard with 41. Do we have a bit of time for questions?
Yep. So it's officially the end of the talk, but you could pick up questions from the thread if you like and answer them. The only thing I would ask is if you're answering something that appears on the Slack thread, then please do say what the question is, because not everybody viewing can necessarily see that.
Absolutely. So Kevin Orr asked whether my definition of I2 equivalence requires some kind of equivalence over E and R. No, it does not. So with respect to the interface E, at this point, we are restricted in the sense that we impose a weak by simulation to match exactly one-to-one with respect to this time Coq equality, the events. So we cannot express interesting algebraic relations between like two different notions of events or sets of events on a single event. So this is definitely a line of work that we would like to dig, but we haven't had time yet. With respect to the return type, which is really what the relation talks about, note that when I say that we have this restriction about events, that means that it prevents us to reason before interpretation, but we can, of course, recover all the equational series that you want about your event after interpretation in the monad, since it moves the state into this return value. At this point, you are free to use any R that you wish, but in particular, of course, we can only prove that the relation, the by simulation is reflexive if you provide an R that is itself reflexive. So you can use a non-reflexive R, but you won't get reflexivity in exchange. So that's basically the trade-off. Jan Stark asks, is it possible to ascribe equational series to the effect set over which nature is defined? No, that is, I have a branch with a very minimalist draft. I would love to do that. At this point, it's not possible. So it goes back to this question, like kind of like, there is this nice paper by Andre Bauer, like what is algebraic about algebraic effects. And indeed, we can like recover a little bit of it in the sense that we conduct this equational reasoning about effect, but only after the interpretation, which is a shame. So we would like to have the weak by simulation itself parameterized by a set of equations, but it is definitely a non-trivial extension, and that is something that we would like to try to do this year, but we haven't had time yet. What are the main goals and of Velum 2? In what way is Velum 1 lacking? So one of the main goals, part of it is that Velum 1 was in need of a refactoring. And so since we had new tools, it was the opportunity to use them. But maybe a better answer is that if you think of what was the semantics of Velum 1, it was a small step population of semantics. So in particular, you were parameterized, the semantics itself were parameterized by the whole graph that define your top level program. Which means that if you do a transformation where you substitute a subpart of the program, say 2 instructions by 2 other instructions that you feel are equivalent, then you are basically trying to relate 2 completely different semantics. You don't have any nice equational way to reason about this. So in particular, this makes it extremely challenging to prove transformations such that loop optimization, loop-based optimization. We have the firm belief and hope that with this new semantics, this kind of optimization will be much easier to prove because we are basically able to denote each sub-syntactic component of the syntax in isolation, and therefore to be able to have a compositional lemmas that allows us to prove a strong enough notion of equivalence between 2 sub-pieces of code and lift immediately the equivalence to the whole semantics. Peter Sewell asked, just as an aside, factorization of thread local control flow and pure computation for the handling effect is what we relied on in composite TSO. Oh, that's interesting. Thank you for this remark. I Oh, I not made the link. I should revisit the paper, definitely. Thank you.
There's also a question from Peter further up the thread about how hardwired the exact choice of weak bisimulation is, or the variations of definition.
So that's right. Sorry. So I believe that these are questions that we did not dig in yet, in the sense that we essentially, well, at least myself, maybe some of my co-authors since then has done differently. We have essentially used interaction trees to denote sequential languages on, we have only slightly explored non-deterministic ones. And I believe that as long as you restrict yourself on this, then the notion of weak bisimulation that we have is non-ambiguously fine. You are probably right that things get more complicated later, in which case we would have to revisit the bisimulation, because the definition itself of the bisimulation is quite fixed intrinsically very early in the project. That being said, you can always recover more subtle notion of equivalence by defining whichever equivalence over the monad that you work with after interpretation. So typically, if you have non-deterministic nodes, so events that ask an oracle for a Boolean and decide to take a path or another based on the answer, if you interpret this event into the prop monad, so you end up with sets of I-trees in prop, then you can define whichever equivalence over this monad you wish to work for, which can be one way to recover a richer or more restrictive notion of equivalence. But I believe you're right that there is some thinking to be done as to whether the weak bisimulation was defined is always the right one or not. I am not sure about that.
Okay, thanks. So I think we should close up there, but happy to carry on questions and answers in the thread. And Lilith, if you could stop recording, we'll switch over speakers. Thanks very much, Yannick.
Thank you.
Okay, done. And while the next speaker is setting up, I think we have a minute or so left. I'd like also to say that I just created a channel where people can post sort of workshop-wide comments or questions that we can try to discuss after the last talk before wrapping up. And I'll just start recording now again.
Okay. Hi, can everybody hear me okay?
Yes, I can hear you and see your slides. If you could wait, a minute, 30 seconds till we hit 10:02 before we start, but we should be fine.
Okay.
Welcome all to the final session of the REMS DeepSpec workshop. I shall post a link to the thread for questions and answers in Slack onto the chat. And Andres our speaker, Andres Erbsen, may also be pausing to take questions partway through. He's going to speak on verified IoT light bulb. Andres, thanks very much.
Hi, I'm Andres. I'm presenting work done at MIT with my coworkers Samuel Groder, John Monjoy, Clark Wood, and Adam Chipala. And the overall goal of this project is to build a versatile system for verifying and building embedded systems against rigorous specifications that describe application behavior in terms of the hardware description language specification of what the system is. So while we do use intermediate layers for specifications of library functions and the language in which those functions are written and the instruction set, we try to state an end-to-end theorem that links the behavior of the application to the description of the initial state in terms of the lowest level, which for us is a hardware description language, without referencing any of the intermediate levels. And this talk is partly provoked by the completion of the first demo with such a proof. We made a Ethernet-controlled IoT light bulb, which I will elaborate on shortly. But make no mistake, this demo exists for the project, not the other way around. The main interest that we take here is in the intermediate specifications and components linking them. Similarly to DeepSpec and REMS in general. However, we differ from many other projects within the DeepSpec and REMS umbrella in that we make opinionated choices about which interfaces we choose and how we model them. And we do not try to capture the full breadth of systems out there. In particular, we have a strong focus on embedded low-level systems. However, we do exercise those interfaces from both sides whenever possible by having different people write the two programs on the two sides of the interface. And for the processor that is described in the hardware description language that implements the RISC-V instruction set, we started from an existing component published at ICFP by one overlapping author with this work. Now, throughout this talk, I will first start describing the hardware description language and the processor we inherited from Okami. Then I will give a brief overview of the trace predicates we use to specify interaction behavior. And then I will explain in detail how the two apply to the demo light bulb application we verified. After that, I will pause for questions and return to the intermediate layers, which I believe are as interesting, although they do not appear in the end-to-end theorem we proved. The Okami hardware description language describes a circuit as a set of modules, each of which contains some registers that store state and some rules that are executed one at a time in an atomic fashion, but unknown order. So at the bottom of this slide, we can see an example from the Okami paper, where initially there is one register containing the value V, and the program executes by reading the register, calling an external method enqueue with the value that was read, and then writing V plus 1 to the register. And here, the label on top of this trace, the enqueue of V, with the value V being included as a part of the label, constitutes the external behavior of this module that we will later be applying verification to and treating as a part of the trace, whereas the registers are the internal state. Now, the main case study in the ICFP 17 paper was to verify a multi-processor system consisting of pipelined RISC-V cores. And while our current system only uses a single core, we were able to reuse a good lot of that proof and make our own modifications only when necessary. Yeah, the traces are made of those labels shown here. And concretely, the processor interacts with the outside world by doing stores and loads to different addresses in the address space, which may or may not be mapped to memory, as we have heard throughout the earlier talks here as well. But we do model the memory addresses specially. In particular, we attach the Okami processor module to the Okami module representing the memory, which internally responds to all calls that ask for load and stores to be performed on memory addresses with the appropriate return value, whereas calls that represent I/O are left as external to our system, so they are not interpreted. And those calls form the I/O trace of our demo example and probably for the next use cases to come. Here's a concrete example. What is going on here at a high level is sending 2 bytes over the SPI peripheral, but the traces in our system are described at the interface between the processor and the outside world. So the implementation of the SPI peripheral itself is not a part of our trusted code base, and we just capture the trace before it, and in particular the trace between the processor and SPI peripheral, that is in terms of loads and stores. So first, a load returns 0. We see that the SPI peripheral is ready to send the next byte, and the processor performs a store at the same designated address. The address here represents the SPI peripheral, and then it stores 1 byte, its value 42. And then when it reads the SPI peripheral's same address again, the read now returns the highest bit set. Note that it doesn't return the byte that was written. That is not how this address works. And since the processor knows the highest bit is set, it should not try to send another byte and just polls again and sees the highest bit is set this again and again. And when it finally reads that the SPI peripheral is willing to accept more data, it can again send the next byte. And the entire behavior of our application is described in terms of predicates on traces, such as the one shown here. So while our application might exhibit many different behaviors, we prove that all of them satisfy some predicate that we write down. Now, just to recap, there are 2 fundamental interfaces that appear in our top-level theorem. One is the hardware description and the semantics of the hardware description language in which our circuit is described. If you are interested in how it's implemented, the hardware description language is given semantics as a labeled transition system in a set of inductive rules given in Coq. And then everything from there up, including the pipeline implementation of the processor and the compiler, which includes simple optimizations like register assignment and redundant computational elimination in branches, are verified. And this further includes application code and drivers that do low-level memory management and other non-trivial things. The behavior of the system is described using trace predicates, which are relatively straightforward, and we sometimes use combinators from regular expressions to combine them, although the language itself is more general and allows for existential quantifiers. Now, just to make this more concrete, I will walk through what exactly this means in our light bulb example. We start with the Kami processor running on an FPGA. So that's in the picture on the bottom right here. If I can refine my mouse, that's the FPGA. It is on a development board that mostly contains a lot of nothing, but importantly, it is connected to those wires to an Ethernet controller on an Ethernet controller development board, and thus can interface with the outside world through this Ethernet cable. And in this case, it only receives information. Separately, on the right, there is the light bulb that is being controlled. Now, in terms of what we prove, what matters is the interaction between the processor inside our FPGA and its peripherals, some of which end up representing the light bulb and some of which end up connecting to the Ethernet. For each of those peripherals, we write a specification of how MMIO traces map to the actions of that peripheral. And in the case of Ethernet, we combine multiple actions over the SPI connection here to represent one interaction with the Ethernet card, which in turn is used multiple times to describe the entire reception of an Ethernet packet. So if we actually run this system, we will see that if you send a byte, a single byte containing a 1 at the appropriate port to the system, our processor will receive this packet and turn the light on. Send 0, the light will turn off. And these interfaces here are a rough visualization of what we proved, because the wires are not modeled. What is modeled is the MMIO interface that causes the SPI peripherals to send data over those wires. But regardless, for what the actual interface is, there is a lot that is outside of this interface that I would like to emphasize. For example, receiving arbitrarily broken Ethernet packets should not be able to make our system to do something other than to turn on the light bulb or to turn it off. And this rules out code execution attacks or just even simple denial of service, because if an attacker was able to cause our board to send out Ethernet packets, it would surely be able to turn on the light at a time where it was not supposed to, or to never turn on the light even though an appropriate command is received. And if we look at the interaction that I just animated, it started by receiving a 1, turning the light bulb on, and then one could imagine that the processor polled for another internet packet and saw no packet. And then it received a 0 and turned the light bulb off, after which an attacker tried to send a malformed message to our system, which was treated as a reception of an invalid packet, to which no response was necessary. And now each event in this high-level log really is a predicate describing a sequence of low-level steps, just as I showed in the concrete trace earlier. Now, for the next several minutes, I will slowly walk through the exact theorem we proved about these interactions. First, we need to start by describing the system that we're going to run. We quantify over all possible initial memories, but of course, the memory can't be fully unspecified, so we require that at address 0 contains in the appropriate RISC-V encoding the instructions generated by our compiler. So here, lightbulb inst was computed inside Coq by running our compiler. Then we consider an arbitrary behavior in the COMI labeled transition system sense of running the 4-stage processor with that initial memory from an arbitrary initial state other than the memory which we constrained. Then we get some trace T, and we say that this COMI style trace must be related to MMIO trace in the format that I discussed so far. And this relation is very simple. It just translates between 2 trace formats used in different projects. And the MMIO level trace must be a prefix of a good trace, where good trace is our application level specification. And when is a trace good? Well, first it must start with a boot sequence, even though it is not particularly important for the FPGA demo. We will get back to the necessity of this later. And then it will consist of an arbitrary number of repetitions of the basic action of this system. Each time it receives a packet containing a command B, where B is an existentially quantified Boolean variable. This is something you cannot do in a regular expression, but which is allowed in our trace specification language, followed by enacting the command B on the light bulb. Alternatively, the system might receive an invalid packet that it is not possible to parse as containing a byte B, in which case we actually prove that this packet does not have a valid parse, and the reception of it does not trigger a light bulb command. Or in the most common case, the processor will poll the Ethernet card and learn that no packet has been received. Now, I would like to pause for questions and clarify, if necessary, what we proved so that we can proceed with confidence to discussing the intermediate layers.
So looking at the Slack channel, actually, we don't have any questions yet.
Wow.
So we could just move on. It's a good, clear explanation. I'm sure that's
people
fine.
actually understood, as opposed to missed me totally.
Yeah, we looked at the demo.
Well,
the light went on, the light went off.
I'm glad. Now, in the remainder of the talk, I will be digging into the intermediate layers. And one principle we try to hold true throughout this work is that we used existing production test interfaces whenever possible. We didn't necessarily pick the existing formalizations of them, but we try to maintain a baseline of realism anywhere where we went. So for example, our Bedrock 2 language is similar to C, but it's not exactly C. Care needs to be taken when translating C code into Bedrock 2. It is often not that difficult, but the features do not match one-to-one. At the same time, pretty printing Bedrock 2 as C, and then compiling that resulting C code with GCC with some permissive flags, we believe results in an accurate representation and practical example of the same program runnable in C. And this is very convenient because we could write the program in C first, test it using traditional methods and even use GDB and existing tools to debug it before messing with Coq at all. Similarly, we use the RISC-V specification developed at MIT PLV. It is written partly in Haskell and partly in Coq, the Haskell parts being translated to Coq into using HS2Coq. And this specification actually tries to be faithful to the existing RISC-V ISA, and we were able to make use of this by first bringing up our Lightbulb project on a commercial microcontroller, doing a bunch of development on it, and then transferring it to run on our own FPGA-based system. And similarly, you can take binaries compiled with GCC and run them on the Kami FPGA, and they work as well. So while those interfaces do not appear in our top-level theorem, we do take great care of them and see them as important for less comprehensive verification, and with still providing interoperability. One great advantage of using a commercial chip with the same code is that this chip has an off-core debugging facility where you can stop the program halfway through and single step it and so on, which we did not find on the Kami research processor. And in fact, in the demo I showed earlier, right in the middle of it, the commercial chip was hiding. It was taped onto the Ethernet controller and provided the situation I just described. And of course, it didn't participate in the actual execution of the demo, but the same demo does work if you remove the FPGA and run our Bedrock 2 code compiled by our compiler on the Sci5 chip. However, when we were formalizing spatial the two interfaces that I just discussed, we hit the difficulty with maintaining the property that each layer is self-contained while capturing the realistic behaviors we would expect any sane implementation to include. And I'll start with what went as expected. So we were transcribing various parts of the RISC-V spec. We wrote Coq code that, in this case, describes how integer division and multiplication instructions work. And that went fine. But then we found places in the specification where some things are left explicitly unspecified. For example, essentially anything to do with input and output is given by the execution environment, not the RISC-V spec. And this makes sense. The different systems on a chip have different I/O peripherals available, and there is no reason to specify all of that in the RISC-V specification. And the microcontroller we used, in fact, does come with a detailed address space map and prose description of the semantics of loads and stores at those different addresses. So we transcribed it to Coq. We transcribed the common behavior, the non-IO memory behavior, and the IO memory behavior. And in the case of just MMIO, the most critical thing to include here was the actual address spaces that are included in IO, and that the accesses to them will be included in a log. Now, at the Bedrock 2 layer, encapsulating this presence of low-level memory mapped IO was slightly more tricky. In particular, it is not fine to just use normal memory access instructions. Here in Bedrock 2 we have store to access memory mapped address space, because we want to give the compiler the flexibility to optimize memory loads and stores that do not correspond to MMIO. Instead, we model MMIO as external calls, which is a syntactic construct distinct from normal internal function calls shown above, but containing the same amount of syntactic information. And the semantics of those external function calls are left as a parameter of the Bedrock 2 semantics, although the syntax is concretely provided. Now, just to understand how this semantics is defined, let's walk through a couple of cases of the Bedrock 2 program logic, which is distinct from the semantics, but we prove the program logic sound against the semantics. So it is fair to study the program logic to understand how this parameterization is achieved. And I believe the program logic is easier to look We give the Bedrock2 program logic in terms of a set of verification conditions. And the verification condition generator takes as arguments the command for which the verification condition is generated, the state represented by the trace T, memory M, and local variable values L, and a post condition P, which we wish this command to satisfy. So if you read VCGen TMLP, it is really a weakest precondition generator. It returns what you need to prove to know that running C from state TML finishes in state P. And we require full termination from those programs. An infinite loop does not have a VCGen proof for any P. Now, in the case of an assignment expression, you will need to show that if you call the verification condition generator for expressions, then it says that E evaluates to V, and the post condition holds with the same trace as so far, the same memory as so far, but with the local variables updated to include the value V for variable X. For the sequence, we will need to make the use of this post condition P internally in the VCGen. In particular, we will call VCGen on the first command and pass as the post condition the lambda that evaluates VCGen on the second command in the sequence, using the trace memory and local variables in the post condition of the first command. And the overall post condition appears in the post condition of the second command. The handling of memory stores, which I will shortly contrast with the handling of external MMIO calls, is relatively similar to assignments above. In particular, the expression evaluation that was shown here matches this line in the beginning of memory stores, and the address is evaluated similarly. Then there is an important verification condition that the address for which the store occurs appears in the Bedrock2 layer memory M. And we make sure to instantiate those semantics with memory that does not include the MMIO address space, and also does not include the unmapped addresses, and it even does not include the program code generated by the compiler, because it shouldn't be possible for this definition to model self-modifying code. The system is not ready for that. Our compiler would not work correctly. Now, here, since this store goes to real memory, we just continue execution with the memory that is updated at this address. But if the standard store syntactic construct in Bedrock2 had been used to do an MMIO store, this line would not be provable. The address is not in real memory, and thus the program would have undefined behavior. Instead, if you want to do an MMIO store, or MMIO load for that matter, it needs to be written as an external call. And here I'm showing the case where we have only one argument to the external call, and then the external call returns exactly one value. This doesn't match either MMIO load or MMIO store, but I believe it is illustrative enough. Again, first, the expression for the value being passed as an argument is evaluated. And then the verification condition generation calls out to a parameter. Here I call it VCExtern. It is the part that specifies what the external calls do. And for MMIO, there is a relatively simple definition of it, but we try to keep our stack general and parameterize over it in a way that we later hope will also be useful for DMA. After the external call, so this is this line, the execution continues with the local variables updated with the return value in the appropriate location, and the trace of external calls updated with the argument value and the return value and the name of the function. Now, so far I just said that the external calls are specified somewhere else. Now let's talk about how we actually specify them. Here I've made up a simple external call that I believe illustrates the crucial features of these specifications. If you call the external function arbitrary below, the caller, so here the person verifying the source code Bedrock 2 program will need to prove that the arguments to arbitrary below have one number in it, and this number is non-zero because arbitrary below wants to return something that is less than that number in the unsigned sense, and thus otherwise its job would be impossible. And then again, the caller, the person verifying the code of the function that calls arbitrary below, will need to prove that for all return values of arbitrary below, the rest of the program will be executed as desired. So P probably here, this P here would probably be another call to VCGen, similar to the sequencing case up here. Or it could be the final post condition of your function. That this P works correctly for any value of R, but you get to assume that this R is less than B. So if you wanted to highlight here the precondition and postcondition of this external call, then this would be the precondition, and this would be the postcondition. And now, it is actually important here that this external call is not vacuous, that it actually sometimes does return. And we prove this administrative condition relatively automatically for all of our specifications. And thus we needed to actually make use of this fact that B is required to be proven to be greater than 0, so that this function can always return an R that is less than B. When verifying the compiler for these external calls, we again need to deal with our usual decomposition. In particular, we wanted to prove the compiler once here in this slightly illustrative, not quite exact code snippet. The overall compiler is represented by the function compile. And the compiler for external calls, compile X, is passed as a parameter for it. So when the compiler hits a node that says X equals external call, it just calls out to compile X here. And the sense in which the external call compiler is correct is in fact the exact same sense in which the overall compiler is correct. The source program has well-defined semantics according to a semantic definition very similar to the VCGen that I've shown you so far. Then the compiled program needs to have the same behavior, or at least a subset of the behaviors. Or alternatively, any invariant that holds in the source level must hold in the compiled program. And this, in fact, worked out to the standard definition of compositional compiler correctness, where we apply the same notion of correct on both levels. And we did it in an ad hoc way first. We are now very convinced that this strategy of using the same definition is, in fact, a good idea. Now, I did not yet show the actual verification condition for MMIO. And it is rather delicate. We spent a good amount of time figuring it out. And the reason it's delicate is that it doesn't quite clearly belong in any individual layer, but we finally split it up between the layers in roughly the way I described. And the reason why it is particularly tricky is that there is instruction caching going on. And you would think, what does instruction caching have to do with memory mapped I/O? But it really does. So the key effect on instruction caching on program execution is that if you write to some memory address and then try to execute this memory address, the previous value might be executed because the instruction cache or the pipeline in the case of the Kami processor contained the previous value, and thus the value in the memory just was irrelevant so far. We work around it in the compiler by proving that the compiler generated code always remains fresh in the instruction cache, that it's never stale. And that is, in fact, an invariant for all code generated by the compiler. We currently do not allow self-modifying code using this compiler. But it is also important that the external calls and the compiled versions of external calls preserve this invariant. And MMIO, if actually targeting the MMIO address space, does preserve the invariant that all code in the instruction cache is fresh. But if the MMIO call was used with an incorrect address, for example, storing into the code region of the memory, Then the generated instruction, I mean, the compiler just generates a store instruction. The processor will happily execute it and overwrite some code. Then the invariant would be violated. So the compiler needs to require that the external calls preserve this invariant. But they only preserve this instruction cache invariant if their preconditions are met, which of course the compiler has no say to, because the source code can calculate the arguments to the external calls as however it wants. And furthermore, it is the source code that expresses the calculation of the external calls arguments, so its correctness depends on the correctness of the compiler so far. The parametric structure we showed you in the previous slide is a result of trying to resolve this cross-layer concern in a workable way. But it really means that while I showed you on the first slide a nice picture with different layers of a stack, this picture is more illustrative than accurate. We do have layers, and in each layer, we do have a separation of concerns, but there are also parameters being passed between the layers. And when instantiating one layer, you take some parameters from the lower layer and use them to construct the parameters at the higher level. And this is rather tricky. At the same time, once we figured it out, we are optimistic that the same approach could work for verifying DMA. Again, appropriately choosing which memory remains in the source language memory, modeled memory M. In the case of DMA, if you start the DMA transfer in a region, you would remove that piece of memory from M. And then after the DMA transfer is known to be done, you could re-add it to make it accessible to the source program, representing an ownership discipline of sorts. Now, I would like to take some questions again, if there are any, and thank you. I do have some extra slides that I am going to go back to if there's not a long list of questions.
That's great. Thanks, Andres. So the questions in the thread so far. So one is about infinite traces. There is an answer, but I'll relay the question. Mario Caniero asked, how do you handle infinite traces? If they're cut off, wouldn't that be a problem for the regex description if, for example, a request is sent, but the response is not yet completed? And there's an answer from Ken Rowe suggesting this is because of treating infinite traces as a limited sequence of finite traces. Is there anything you can add?
Okay. So we do require that all the traces our system generates are prefixes of traces to satisfy the regex. So if the response is received, if the request is received, the response is not yet enacted, this would be a valid prefix of an allowed trace. We do not distinguish infinite traces. We only talk about any finite trace the system could generate and then apply this predicate to it. And it should apply to any finite prefix of the infinite trace, which sounds convincing enough to me, although there might be some use cases where you would prefer a different characterization.
Okay, thanks. Leonard Bellinger asks about slide 39, compositional compiler correctness. Are there any issues or assumptions with respect to mutual recursion or higher order constructions in there?
Okay. We do not support higher order external calls yet. So we don't have the issues because we don't have the feature. I am sure it is difficult.
Okay, and various kinds of recursion or mutual recursion?
No mutual recursion right now. The recursion, no, there is even no recursion support in the entire stack right now. I think there is a layer that supports it, but it is not threaded through. The reason why we chose not to use recursion in the end-to-end system we targeted is that one of the preconditions you will need to prove in the very top level integration of the system is that the stack space potentially used by this program, which our compiler computes using a static analysis in a conservative manner, actually fits in the available memory. There is really no out. We needed to verify that our stack does not overflow, and the simplest way to do it, in our example that didn't have recursion, was to rule out recursion.
Mm-hmm. Okay. So we're open to take more questions on the thread. I have a question of my own. So from the way you've described it and the abstract, it seems clear that you're attempting to build this in such a way that the components would be either reusable or exchangeable. And this is just the first start of that. Do you have any specific plans for which component you would like to reuse, or what example you'd have where you can replace one component with another?
So we're working towards a more complicated application that would include user interaction more than just a light bulb and Ethernet. That would replace the topmost and largely the second to topmost layer of the stack. Separately, there is ongoing work that I'm very excited about for a new processor description language called Koika that I think is also discussed at PLDI this year. And we hope that once a processor is developed that is a suitable replacement for the Kami standard RISC-V pipeline processor, would be able to connect to the new processor in the new hardware description language from the same RISC-V spec we have verified so far. And we're going to extend the compiler in various ways, although we're not planning to scrap the existing parts of it. Okay, and these will be replacing single components in the stack and keeping the rest as fixed as possible is the idea. Yeah, so far I think there is a reasonable chance of replacing application code and the processor, including the bottom specification. There likely will be new drivers and there likely will be new features in the compiler. Okay. Another question, there's this again from me, the RISC-V ISA you're using, we have, and there was discussions yesterday about a RISC-V model specification in SAIL, which is now being declared the official semantics for RISC-V instructions. And we do have a COC model we can generate from that. Is there anything you think would particularly be involved in switching to that COC model from the one you currently have? Okay. The first comment here is that we started this work before it was clear that the SAIL specification would be the official one. And oh, absolutely. No, I know there were several in play. Yeah, we're coming around background. I think the SAIL specification has some important similarities, especially in the way it handles non-interaction execution in the code. We think the switch would be relatively straightforward. We currently do rely on the ability to parameterize our RISC-V specification over the behavior of loads and stores to non-memory addresses, the same way we parameterize the specification on the Bedrock 2 level. Mm-hmm. I believe that something could probably be worked out there, but I have not investigated it deeper. Okay, right. No, I could see being embedded that the question of how MMIO works is going to be important for you. Mm-hmm. Okay, lacking more questions, I will take a moment on the bonus topic. Thanks. Which is, we also studied the amount of work various layers of the stack took and categorized every line of COC proof in our library. So the focus here is on the left table. The right table is a comparison with other work, which is also exciting, but not what I'm talking about right now. We went through every line in our library and we categorized them as whether they're related to the demo at all. There was a lot of code that was developing MMIO and so on that was not related to the demo. Whether they're a generic COC library that we really wish to see in the standard library. Whether they were other boilerplate like require and import statements. And then we also separately counted Kami, which was previously discussed in a separate paper. And we found that the amount of code and proof we wrote was on par with existing projects in verifying systems in COC. But then when we categorize this proof into interesting proof in the sense of we really don't think of a automation tool could come up with this, or as low insight proof where we kind of know what automation we would want, but for various reasons haven't implemented it, we found a rather dramatic difference. So for example, at the application and driver layer, here this layer contains both applications and drivers, we found that anything other than the loop invariants, in principle, needn't be written by a human, but still we had written a lot of it by hand. So we would like to improve the level of automation, especially on that level. Whereas the semantics definitions often included quite a bit of code, and while they did have some tedious proofs in there, the ratio was much more balanced. And of course, there are some layers that don't have any code at all. So when we do the end-to-end proof, it's hard to say which part of the code it should correspond to. We write the 0 here, though you could arguably say that the 5 lines we wrote to put the code at the correct address is the end-to-end integration as represented in our code base.
There's a question on Slack.
Yeah, thank you.
Where Ken Rowe asks, have you thought about computing a ratio between the effort to develop a piece of code and the effort to verify that code?
So the best proxy we can quantitatively measure to a clear standard is for the effort is the count of lines of code. There is broad agreement, although not great faith in the precision of this measure. Like specifically within our team, we kind of agree that this lines of code do correspond to the amount of effort spent. At the same time, they shouldn't be taken to the third significant figure as they're provided here, but rather as an order of magnitude estimate. We generally found that a lot of the effort was either in totally mindless tasks like finding out why this cock proof runs out of RAM, or in legitimately difficult interface design decisions, as I discussed in the case of MIO and instruction caching so far. Generally, writing application code once the interface around it was decided, or stepping through the proofs for that code in a known environment was relatively easy. So we think that if we were to continue writing applications within the existing space of interfaces we have, we would arrive at the more realistic measurement of what the actual effort breakdown is. But so far, most of the verification effort went into defining the interfaces. So the measure so far would not generalize particularly broadly.
Okay, that's grand. Thanks very much. So we're at the end time now. Thanks very much to Andres for giving the talk. And at the end of the session and the workshop, I'd like to ask Lennart Barringer to say a few words to finish up. Thanks very much, everyone.
All right, thanks to Ian for chairing those last 2 sessions. And also let me start by thanking all the speakers again for giving such interesting talks. Also like to thank all the participants on Slack for adding questions and answering and really helping to make this event very lively and interactive. And thank you for understanding our technical improvisations. So as I mentioned before this last talk, we have a little bit of time where we could maybe discuss if there are some questions or general comments from the audience. I think most PIs are online and many of the speakers or their co-authors too. I haven't seen anything yet on the Slack channel. Let me see. No, there's nothing yet present. of course, so the Slack channel will remain available at least until the end of PLDI, possibly not much longer, but at least for the next few days, you can continue discussing any topics on either in the threads related to particular papers or the general workshop. And of course, we'd then also like your feedback afterwards if you have something else you want to comment on. I think that's, if there's nothing immediately, then I'd just like to thank everybody again, and we can wrap up here. And I wish you all a very successful rest of PLDI.